So it's 10:35, and I think we can start the recording. Deepak, are we ready with the
Yes,
recording?
yes. We can start.
Okay. So welcome everybody to the day 4 of this industry readiness workshop on CFD. I am Payal Mukherjee once again from FOSSI IIT Bombay, and I welcome you to this last day of the workshop. And this last day will be very important because towards the end of the workshop, I'll be sharing the opportunities about internship and fellowship and many more information about case study project, research migration project that we are offering for everybody. So one and all are welcome to participate in the FOSSI project, and how to participate, I'll tell you towards the end of the workshop. So welcome, Dr. Joseph Prabhu. Yeah, thanks. So thanks for joining. So we will begin with a small introduction of Dr. Joseph, and then we can start with the session. So just allow me a minute. Okay. So Dr. Joseph is a CFD engineer with a PhD from IIT Kharagpur, specializing in marine structures CFD. Currently, he is associated with the research division of Indian Register of Shipping. With over a decade of experience, Dr. Joseph Prabhu has a deep understanding of marine hydrodynamics. His research has led to development of numerical solvers, including a potential-based solver for maneuvering dynamics. This work has been recognized through publications in peer-reviewed journals and presentations at international conferences. Dr. Joseph actually also worked with us, with the FOSSI team, on some part of the OpenFOAM GUI that we are developing. And that work has also been published, and it is available for all at cfd.fossi.in. And Dr. Joseph Prabhu is proficient in both commercial and open source CFD software. He has extensive experience in solving a wide range of marine hydrodynamics problems using OpenFOAM. So like resistance and open water characteristics of propellers. So that was a brief introduction for Dr. Joseph. And so over to you, sir. We can start with the session.
Yeah, thank you, ma'am, for a great introduction.
Thank you.
Okay, welcome all. So I was associated with FOSSI team almost for last 2 years. So I have already submitted one research migration project with FOSSI. So, ma'am, on doubt, who are mostly our audience will be students, and who all are there as of now? Payal, ma'am?
So we have a mixed crowd. We have students also, and we have CFD professionals also.
Okay, fine. Okay. So I will share my screen. Hope you can see my screen.
Yes, sir.
Okay, fine. Okay, so myself, Dr. Joseph Prabhu. So I am working in Research and Development Division of Indian Register of Shipping. So we are located in Powai near L&D Junction. So this is our head office. So I'll just start with a brief introduction about my organization. And next I'll be discussing about what our organization mainly focuses on, and then my department, research and development, and what all are the activities we are doing in hydrodynamics group. Then this formation of IRS, it is formed in 1974 as a public limited company. It's the form initiated by the Mudaliar Committee by the government during that time to support our marine industry in the for the development and research purposes. So it made as a public limited company as it should be collaborate with other countries and work in. So it has no shareholders and it is financially and functionally independent, and it doesn't receive any grant from any source. It generates its own revenue. So we have some recognition from Indian administration. So we can assign load lines to our ships in both Indian and other vessels, other country flag vessels. Then we can carry out audit in ships and ports in accordance with international safety and international ship and port facility codes. And we can audit the ships based on the whether it is sailing as per regulations, pollutions, norms, everything need to be checked. So we have 53 global offices, and outside India we have 26 offices, and India we almost cover almost all the ports. And these are the departments. So here we have head of operations, so that they will be doing surveys at the of the ships. They will be boarding the ships and checking for the capabilities and other things. Then technology and innovation, they will develop some softwares that will be helpful for our surveyors. Then we have one training department, and we have rule development associated with research and external. So this department mainly focus on the development of rules, how much ship should maintain a particular speed and what will be the thickness for particular portions. That rules will be development, and this will be followed by the surveyors during their inspections and all those things. Then research and development, where I am associated with. So here we have hydrodynamics and multiphysics, where I am working, and other we have marine and offshores and risk and reliability, then long-term strength. Then we have ships and technical services, classification, certification, and all those things. This classification, certification is the main part of our organization, as almost every ship should be classified by some of the society. Either in every countries almost have their own classification societies. So we will be representing India. So every 5 years they should go to our every ships need to be audited, and every 2.5 years it should be some intermediate survey need to be done to in order to sail it in the international waters. Then plan approvals center. So before building ships, the plan should be prepared by the clients, and that should be well approved with our organization. And then it will go to the yard, and yard will be constructing the ships, and that will be inspected periodically by our surveys. So from starting to till the delivery of the ships, our society will be getting them. So where our research and development, where we focus on these things. So ships have some, if in marine industry faces any problem, some ships due to regulations and some issues, some break, some updation, some ship may go to updation. And as per now, complaints is going on regarding the pollution and carbon reductions. So every strict regulation, they should be not carbon emission should be low as possible. So they need to reduce the improve the ship's efficiencies. So every ships need to be now carried out, improve the efficiency of this in order to maintain the speed to like that. So in the cranes, they approach us to maintain the check for how we can improve the efficiency of the ships. So we recommend some energy saving devices like propeller fin that we'll upcoming slides we will see. So in that way, we will be helping the marine industries. So these are the activities carried out in our hydrodynamics department. So this will be our daily jobs kind of things. So we need to be resistance computation is our basic job for all the vessels. So resistant computation we will be using commercial softwares, CCM, and occasionally we will be using foam also for this. So this template, we are resistant calculation templates we already submitted to FOSI. It is in research migration project. Those who interested can go through it. It is multi-phase flow. So air and water and wave interaction will be there, and ship will be moving at particular velocity and how much is the drag, and we need to obtain the speed power curve. Then open outer efficiencies, that is for the computer the propeller efficiencies. So they will remove the ship. We'll be keeping only the propeller and rotate the propeller at various operation and compute the thrust. This process is called open outer efficiencies. So this is to compute the efficiency of the propeller. So then next goes to the self-propulsions. So self-propulsion is the combined of resistance and open order the things. We'll feed the propeller with the ship and rotate the propeller. And this propeller force is given to the body force of the hull, and that will be moving. So that from that we can complete the efficiency of the ship. Then energy saving devices. So to improve the propulsion efficiency and the hull efficiency and other parameters, there are some energy saving devices like wake fins, propeller duct, and all those things that we'll discussing in later slides also more detail. Then other services we will be doing mooring analysis, some offshore rigs and any tugs need to be more mooring analysis can be done. Then onboard noise. So if this is for normally naval vessels, any noise in the vessel due to the propeller engines and propellers. Then evacuation analysis during in case of emergencies or fire or something, what is the evacuation procedure, and that analysis can be carried out. Then fire and smoke analysis. So if something got fired and the trajectory of the smoke and all those things. Then specialized analysis, we will be dealing with naval vessels. There we'll doing underwater noise, radar cross sections. So RCS will call. This is for the normally naval vessels. We should be away from the. We need to hide out from the radar. So how much we can reduce our RCS signature. Then electromagnetic signatures. So that will be seen in detail. Then ship airwake. So ship airwake. This will be some naval vessels have halo operations. So aircrafts will be landing on the halos. So for that, we need to study the airflow along the halo decks and along the ship. Then underwater blast. So underwater blast means any blast happened at particular distance from the ship, how it will impact our ship. So we'll be seeing details of this. Then ship resistance is our keyword here. So this will be going as a multi-phase flow. So we'll be top air and below it will be water, and ship will be moved with a particular velocities. So using this, we can achieve the speed curve for various speeds. What is the resistance? So we'll be having more benchmark studies like model test, and based on that, we'll validate our CFD results. So there will be template approaches for that. We will having ITTC International Towing Tank Conference guidelines will be there. So that will be followed. And domain dimensions, how much domain we need to pick forward after everything is given by ITTC. You can follow that easily, ready-madely. Now open outer efficiencies, like already I talked about some things. So how we'll be keeping behind the hull, remove the hull from the ship, and just only rotate the propeller. This will be single phase, only water. It will fully submerged, and we will be rotating the propeller, and we can compute the thrust, torque, and the efficiency of the propeller. And this is self-propulsion. So this will be the combination of both the open outer and the resistance part. So how much RPM is required to propel the ship at a particular velocities. So that will be, so we here the modeling will be little bit critical. We need to make the propeller as a separate domain that will be rotating domain. And there will be two methods, RBM and rigid body method. Rigid body method and moving reference frame, MRF and RBM. Okay. So in RBM, we physically rotate the propeller, and we will compute the forces on the transfer that force to the hull, and ship keeps on moving to overcome the drag of the ship. And MR of moving reference frame, we will keep the propellers static and will make the flow around that fluid particles to rotate in that domain. So that will be two techniques. So MRF approach will be with quicker results and computationally less expensive. But this RBM techniques will be time consuming and computationally more expensive. So for simple cases and where geometry complexity is less, we'll be going with RBM, and we will be in where accuracy and RBM is more accurate, and where accuracy doesn't matter, we'll go with MRF. So these are the some energy saving devices. We can improve our propulsion efficiencies and the hull efficiencies. So first one is the wake equalizing, that will be placed below in front of the propeller. Okay, so video is not playing. So it will be propeller will perform better when we get a flow, will get a proper flow. So some wake equalizer duct can be kept that will regularize the flow to the propeller such that propeller can work more efficiently. Then we can keep some duct around the propeller. Then we can make in the hub, we can make the PBC. Sorry. In the hub, we can keep some PBCF fins attached with the hubs. That maybe also we can improve the propulsion efficiencies. So currently what is going on in the industry means that strict norms are there to ships to that carbon emission should be minimum. It should not exceed to a particular limit. So in order to the old ships that we are built 10 years, 20 years back, normally the ship lives are tend to be 25 years. So older ships, both are older than 10 years, are need to be compliant with this criteria. So what they are doing, so if the ship is normally moving at 10 knots, so they will be having a check on this carbon emissions. So, and based on the tonnage, it should be limited. So if it is emitting more, they should either you reduce the speed or reduce the tonnage of the ship. That will be a loss to the ship owners. So in order to further improving their old vessels, we will be fitting this kind of energy saving devices. So we cannot directly fit to the thing. So for that, we will be using CFD analysis. So they will give the hull to us and presenting what is the propeller available with them, and we will be trying various energy saving devices, and we'll optimize, and the design goes to the yard, and they will manufacture and fit it, and it will be incorporated in the ship, and such that they can maintain the ship ship speed and tonnage, that without any loss they can run the ship. That is the purpose of this energy saving devices in current scenario. Then we will be doing some sea keeping study of planing hulls. So anybody having any doubts, you can stop me at any time. Okay, we can clear then and there, and we can move on. Okay, anyone having any doubts or clarifications? Then seakeeping study of planing hulls. So these are the seakeeping analysis. We keep the move the hull at particular speed on particular waves. So the videos are somehow not running. Okay. So these ROs of the ship motion. So whether this is based on passenger comfort, we will see we will be moving the ship and how much is the maximum vertical acceleration, horizontal acceleration coming on the ship. So for what speed we can go and what waves we can travel, that can be calculating during this. Then these are the mooring analysis. These we do in Moses to compute the floating platforms, how it should be moored, and when some ships need to be in static operations, for that mooring analysis can be, and tension in the mooring lines, need to be checked using Moses. So then another thing, we already discussed a little about this radar cross sections. So our this is normally applicable for the naval vessels. So we need to make the ship to be less exposure. So it's the measure of how detectable the ship is by a radar. RCS is the cross section produced by the reflected rays received by the radar plotted on the circular area. So some we will be putting some we will be regulating this in Alter FICO software. So we'll place them pass them radar rays at all the 360 angles, and we'll find out the exposed area and which angle it is more exposed we can computize. And our main aim was to reduce this RCS signature. It should be less. So we can make the body geometry less such that it will be reflective, or it should be the rod ray should be absorbed in. So higher this cross section area is the detectability of the ship. So for this process, we need to model the hull first, and we need to make a proper mesh, and we will be passing various RCS signal frequency, various frequencies like the range width, and we need to material properties also assigned to the hull bodies. So based on that, we can get the RCS signature around the hull for all the 360 degrees. So you can see at 90 and 180 we are maximum exposed, and at 0 and 180 less exposed. So after computation, then how we can minimize this, minimize this. So there are some equipments, some RAM equipments will be there. So we can fit it at wherever it is maximum exposed. We can observe this radar. So we can bottom graph, you can see the with equipment is less at the blue line is peaking out 60 in the range, and that can be when after fitting this equipment we can minimize it to almost 0. Then hotspot identification. So which part of the ship contribute to the highest mean of the RCS? So based on the geometry, it will be giving the hotspots. So we can work on that particular area and reduce the RCS. So how we can minimize this RCS effect? We can target by shaping. The shape should be maintained such that it will be it should not be reflected back. And deployment of screens, application of radar absorbent material that is called as RAM. Active passive cancellation techniques will be there. Then surface treatments. So these are these for 1 gigahertz graph, we can see the for 0 to 360 what is the RCS around the hull. So after fitting that radar absorbent materials RAM, you can say there is a reduce in the RCS effect in the hull. The static magnetic signature. This is actually whenever a ship or big mass of iron metals are crossing the ocean, that will disturb the Earth's magnetic signature, and that will be sensed by the mines underneath, hidden by the enemies. So that will be triggered based on this disturbance of the magnetic fields. So sea mines are the major threat to the vessel operating in littoral waters, and electromagnetic signatures which governs susceptibility to sea mines is predicted based on electronic conductivity and magnetic properties of the hull. So effect of equipment, weight, vessel motion can be accommodated in the advanced studies. So currently we are not doing that weight and all those as activities cannot computed in our present software. So this can be minimized by placing, you can see that will be in upcoming slides, I think so. So numerical modeling of this thing. So first we need to model the hull and where propulsion plant, everything need to be detailedly modeled. and then we can find out the electromagnetic flux. So you can see the as Z both in X, Y, and Z components, you can see the electromagnetic signature along the length of the hull. So you can see, so how we can avoid these things by making coils in lengthwise and in horizontal ways and in transverse ways. By keeping these coils and counteracting that electromagnetic signature, we can nullify this effect. So such that this signature will not identify the minds behind it, beneath that. Then that is by that we are completed with the RCS study, and now we have some specialized analysis for the naval vessels, that is airwake analysis. So here the flow will be only single phase. We will consider only the portion above water. We will take it as a single phase, and only air we will be blowing it in the top and computing the airflow along the cross section of the ships. So first we will be having new model test. We will be doing model test in some of the facilities available in India, and we will validate it with our CFD. Then we will proceed further. The main proper motto of this study is we need to find out the safe halo operating limits. So at what will be the operating limits of the halos land? The aircrafts need to be landed in this halo region. So for that, what will be the safe operating limit that will be designed? Any short circuit of funnel. So there will be plume coming out of the funnel, and that should be smoothly pass away behind it, and that should not be entered into any of the engine intakes. That should be also monitored. So this is the wind tunnel modeling test. So first this is 1:50 model of our vessel. So this wind tunnel facility we will do it in IIT Kanpur. So there will be the model will be printed it in 3D printing. Then it will be assembled, and then it will be kept in the wind tunnel, and it will be the exercise. Then vessel velocity will measure at the in PAV. Then the model will be rotated at various headings and compute the flow along the hull. So this will be the computational domain. So this will follow one L length forward of the ship and 2L behind, and along the sides we'll make 1.5 and top we'll make 1L. And domain, this is the domain dimensions. Then observation planes. So we'll be having vertical planes, horizontal planes, and transverse planes as in the images. Along the halo is our main focus. So we'll making few planes in that halo regions, both vertically, and we'll be horizontally also will be keeping, and transverse ways also be keeping, and we'll be measuring all the three components UVW of the velocities. Then for validation purpose, from internal we will be getting the contour plots at these planes, and that we will be pointing out, we will be keeping probes in the CFD things, and we will be check one by two how it is deviating from the experiment, and we will be trying various numerical models like K omega, SST, epsilon, like spallout alarms, like that various things we will be trying, and we need to fine tune our model to match the wind tunnel. And then in wind tunnel will be very expensive way, so we can't do all the test in wind tunnel. So few tests we'll do internal and validate with the CFD and fine tune our model for proper mesh count and proper turbulence model. Then we'll run for all the oblique angles of the headings. So validation procedure, we will be doing one-to-one validation. So this left side image, you can see it is got from the wind tunnel. They will be taking some few after when the flow is normalized or smoothened. They will be averaging the frames of 300, and they will be getting this contour. This is the hollow portion of this and in CFD we will be getting this CFD. This flow is leads to highly unsteady, so we will be finding, so some iterations it will be more, we won't get this match this, so we need to find out which to, then we will be checking that iteration, and validating purpose we'll use that frame. This is U component and the streamlines are overlapped above it. Then flow separation zones need to be computed in the halo regions. This is important actually when helicopter is trying to land behind the things. So any flow is coming and any circulation happens in some reverse flow. It might be sometimes whenever you might have seen many accidents have happened while halos are trying to land. While landing, that is a very tedious process for the pilot to land properly on the halos. So this is main thing is that because of this circulations, if some circulations or some sucking flow is there, means it will be pulled out and it will be crashed in the hull. So to avoid that, this study is made to find out the at what zone it is circulating, and if it is severe, we need to avoid that conditions to land it. So this is the safe operating limit. So this need to be prepared. So ALH is one of the helicopter's name. So first we will compute that various planes. So Z equal to 1, like from the above, from Z equal to the halo level, from that 1 meter height, 2 meter height, like various levels, we will be computing the velocities. And wherever we'll check further if the velocity is at headwind and the crosswind and tailwind. So three things need to be said. Headwind is wind is coming from forward, crosswind is 90 degree, and tailwind is from behind. Tailwind is from behind. So we need to check this. If it is exceeding, every helicopter has its own capacity and limits. So we need to check further. If it is exceeding beyond that, we need to mark it with the red portion is the it is limit is exceeding. So this particular case need to be avoided. Then temperature at critical equipments. So some equipments placed at the in this ships may be very critical. Some sensors will be there, radars will be there, everything. So when our plume comes out of the funnels, that will be passing and heating up this area, and that sensors may be affected. They may not perform properly due to this. So we will be perform a plume analysis as plume is exiting from the funnel and it should be smoothly pass it from the beginning. Due to some circumstances or some wind flow oblique angles, it will be pulled back and hit it in the mast, and that increase the risk of the damage of the sensors. So this need to be studied. This need to be studied for various flows and various oblique angles, and we need to plot like that and check the temperature. So every sensor's limitation need to be noted, and we need to be checked like this. Then the plume analysis, main focus of the plume analysis is to check whether the plumes are passing smoothly and exiting via the aft. But in this image, you can see there will be some circulation. If the bluff body is there, there is a low pressure zone. So flow will be coming in, plumes will be coming moving to the forward. That is heating up our sensors, and there will be intakes also for the engine rooms. Engine need to intake air from air, and it will be exhaust to go in. Sometimes what will happen means this exhaust will be circulate and again it will goes to the intake. So that will reduce our engine performance, and it is bad for our engine operations. So that should re-entry need to be avoided at any cost. So for that, this is the purpose of this plume analysis. And another thing, this plume will be exposed at higher temperatures. So it should be, as naval vessels need to be, signature should be kept low when operating at other enemy territory. So we need to keep the reduce the temperature. So temperature need to be monitored. So if you are operating at risky zones, we should not be caught by our enemy things. So our signature should be kept low. So that temperature should be monitored. If the temperature is higher, we need to use some other measures to keep it low. So for that purpose, you have seen in the below image, we are measuring the temperatures along the keeping the planes in the along the cross section, and we are measuring the temperatures. So we have some infrared signature studies also in the we'll be doing. So based on that, that engine room temperature and everything should be minimized. Then shear flow analysis. So these images will show that shear flow when flow is coming. So beyond the bluff bodies, there will be circulations of the things. So that will be necessity for keeping the major equipments like some anemometers will be there. So for performing some operations in the ship, we need to be know the velocities and to be maintained like that. So for that we can important. So this first image is beyond the funnel, and this is beyond the mast, and this is in the halo deck. So how we can see the vortex is rolling around. So that will make the halo operations difficult. So like this, we need to do it for various angles and various speeds. So there is, it will come with a matrix of the cases need to be run in CFD, like various heading. Every 10 degree will be 10 degree, normally 15 degree will be keeping rotating, 15 degree, 30 degree, 45 degree, like that oblique angles will be rotating. And we will be increasing the 2-3 variation of 10 knots, 20 knots, 50 knots, like that various speeds will be trying out and computing which case try to be avoided, and finally we need to list it out what are the cases need to be avoided and for the operations. Then anemometer is the one thing, as I already discussed regarding this. Anemometer is measured to the velocities at velocity of the ship. The ship is moving at particular 10 meter. In this image you can see if it is moving at 10 meter per second, anemometer should be measure it as 10, but due to some obstacles forward or behind, it may not be, it may fail it some cases. So we need to plot it like a polar plot. At R0 means wind is, ship is heading in 0 degree, wind is also coming. So this anemometer 1, and there will be various anemometers in the ship. So at what angles, if ship is heading, wind is heading at what angle, with anemometer reading we need to take. So various anemometers will be there. But if you see anemometer 1 is good at R15 to R30 to R30. So whenever it is 30 degree variations, anemometer 1 will be good. But other headings, these are over predicting the velocity. So 10 meter per it will show 11, 12. And even the wind is coming from the aft, it will be only less. It will be 50%, only 5 meters instead of 10, it will show 10. So like this, we need to calibrate it. Then anemometer 2, if you see, it may be in some other locations. It may not be good at all the particular headings. Some headings it is giving good, and some heading it is not giving good. So like that, we need to, will be various anemometers on the ships based on the operations. So thank you from my side. So anyone having any queries, I have time to take some questions.
So there's one question in the chat. They were asking, how did you model the movement of the ship?
Okay.
Yes.
So there we can do 2-3 ways are there. We can make it as a sliding mesh, and we'll put it as the hull in one particular domain, and that will be moving. Sliding mesh we can do. Else in this purpose, Normally for resistance, we won't move the ship. For sea keeping maneuvering, we will move the ship. In that, one mesh will be moving with the ship. You can see from this slide, the ship has a separate domain that will be moving domain that will be moved with the ship. So, and that will be moving into another domain, another computational domain. So this is for sea keeping. That sliding mesh technique we will be using. And for normal resistance and all those things, we won't move the ship. Ship will be as a fixed, it's a rigid body, and only the flow will be there. Is it true?
Yes, sir. Thank you, sir.
So currently in open form, we can do resistance and even open water we can do. And I am currently working on how to find the self propulsion and other things. And we works on Helix also. It's an open source tool. They have some GUI based open source tool, but if I want GUI, we need to pay for it. Script based we can use in Helix. And other things normally will for ready. Our works may be daily one on new variations will come. So for quick solutions, we will be using CCM. So those who are students, you can get my anything. You have any questions or something, you can talk to Payal madam, and you can communicate me any queries, or you can work. If you any students are interested to do some projects with us, collaborate. Ready, I am ready to, and our organization is ready to welcome. It's near. We are located nearby. It will be easy for our commuting and other purpose. You can consider for a BTech 6 months projects or something. Any one of the projects we can develop in form. But we already discussed with Fileman. So any students or anyone interested, we can have a paid internship also.
Sir, there's one more question in the chat.
Chat, okay, I can't able to say. So what are the optimized location to place ESD? So normally fins will be there. That will be mid hull, from mid hull to till 70% of the hull. We can stabilizer fins will keep. That will make the flow steady. That is one of the thing. Then wake equalizing that will be forward of the propeller, and rudder boss cap fin will be there. So in front of the rudder there will be one cap fin behind that will be linked with the close to the not touched, but it will be take the flow from the propeller. So that basket fin. So based on that, how we will design means based on the current geometry of the hull. So current geometry of the hull goes to old vessels. So hull we can't do much modifications. So based on the hull, how the flow is coming to the propeller, so we can try. We normally try all the variations, and we will say this one, which one will be better. So some ships may be basket fins may serve the purpose. Propeller basket fins will be there. That will be keeping behind the propeller, and some may keep the equalizer duct to regularize the flow. Like that we can try it in CFD, and we can find out which is the optimized way, which one we can keep. Yeah, we can the internship be done remotely? Yeah, you can do, but you can come to once a week or something. You can come once and take the problems. We can discuss further. If you are in IIT Bombay, then it is close by. It's hardly 1 or 2 kilometers. You can come. It is not you need to full time. You need to stay here or like that. You can work from your
Yeah, I think online also they can do the internship, right?
yeah, we can do it. No issue.
Actually, for FOSSI internships and fellowships, CFD professionals like Dr. Joseph actually guides the students also. So last time also,
Yeah.
Dr. Joseph has floated a problem, but unfortunately, we couldn't match that problem to
Yeah.
the applied the students who were selected. So maybe this time, if some of them are applying for the next fellowship, we will be announcing around January to 2026.
Okay, ma'am.
Then we can
It will
arrange
go as a internship or it will go as a project
internship.
like internship. Okay, okay.
Internship for 3 months.
3 months.
I
Okay.
mean, because people, what they do is, if the problem is not possible to, be finished within 3 months, then a preliminary kind of report can be submitted
Okay, okay, okay.
at the end of 3 months, and then that work can be carried forward, and people actually take it forward to publish it in conference proceedings, in
Yeah, understood.
book chapters, journals.
Mm.
So it's up to the guide who is guiding the student and the intern who is actually taking up the project.
Yeah,
Yeah.
nice. So it's nice if you any students willing, you can ready to if they will like our organization and if our organization likes them, we can observe them here also, no issue.
Yes, true.
Okay, I mean, last time we done this in offline, na? This program, the same thing or file, ma'am?
Yes, last time actually in a year we announced it twice or thrice. So this time we have announced it 3 times a year. It
Okay,
was
okay, fine,
announced
fine.
around January, so we have commenced around February, March.
Okay.
February, I think. Yeah, February. It was semester-long internship, totally online for 3 months.
Okay,
And
fine,
then
fine.
another fellowship was announced. It was for the summer months, 2 months. Okay, so
Fine.
it was from May to June, but people actually drag till July, August because the
Ah,
2 months. So some of them submit, but some of them they have some exams and some other commitments. So if they are working good, we can give them extensions.
yeah,
And
fine.
now at present, the autumn internship is going on
Okay.
for only for CFD. I mean the
Okay.
hardcore CFD part and the open form part, and the open form GUI part will be taken up as winter internship in December.
Okay,
So
fine.
actually that is going on now. The registrations are going on for open form GUI part only. We are not floating
Okay.
open form core part for the winter internship.
Okay,
We'll be announcing in
fine.
January again.
Okay.
Hmm.
Okay, ma'am. And then if there is no other questions, any next speaker will be joining?
Yeah, actually we'll be having a demonstration part, a hands-on training part after your talk. So
Okay.
if there are no more questions, we can go ahead with that.
Okay, fine.
Okay.
Okay,
So
thank you,
thank you
ma'am.
so much, sir. Thank you
Yeah.
for joining. It was
Yeah.
a very informative session.
Okay, thank you, ma'am.
Yeah, thanks for joining, sir.
Yeah.
Bye. So, Evan, are you ready for the hands-on part?
Yes, ma'am.
Okay, then over to you. Please carry on.
Yes. Okay, so I'll share my screen. Okay, so is my screen visible?
Yes, sir.
Okay, thank you. So again, welcome back to the industry readiness workshop. So for the case study demonstration that we have, we will be demonstrating a multi-phase simulation on ship resistance. We also have one more case, as Professor Joseph Prabhu, Dr. Joseph Prabhu was saying that he has submitted one research migration. So at the end of this session, I'll show you that case as well. If time permits, we will go through the whole case. So let's begin first with this case. So first you can head on to the website. You can go to case study project. You can go down to completed case study and you can scroll down to case study number 131. Okay. So this one. So multi-phase simulation using OpenFOAM to calculate ship hull resistance. Okay. It's done by Mr. Rishabh Sharma. So you can download this case study. We will go through this whole case study right now. Okay. So you can download. So once you download it, yeah. So once you download it and extract the whole thing, you will have this one abstract and you will have the case files itself. So within that, you have multiple case files. Now over here, in this particular case, they are finding out the coefficient of drag or the drag force that is applied on the ship hull itself. Along with that, they have also compared four different schemes in multiphase. So you have the Eulerian scheme. Since they're using volume of fluid, there are these four schemes that they're comparing. So you have Eulerian scheme, then you have Crank-Nicholson, local Eulerian interface, and the MPLIC one. Okay, so let's see what are the difference between these and what are the advantages and disadvantages of using these. So back to the PPT. So again, we are using this case study. So before beginning, for people who are not well aware of basically the parts of a ship, the hull is the lowest most part of the ship, the one which is in continuous contact with the water itself, and the one that faces the most amount of forces. Okay, so every time a ship passes through the water, this is the first place where you will get the most amount of force. So this has to be the strongest. So we are calculating the force acting on this particular area. Okay. For this, we have in the case study a simplified version of the hull. We don't have anything on top because we only want to find out what exactly is happening at the hull area. Now, in case you want to import your custom STL file and generate a simulation for the whole ship you have, you can do that as well. So for our case, we have a simplified version. This whole geometry and mesh is created in Snappy Hex Mesh. So we'll look at that as well. Yesterday we had a session on Snappy Hex, so we'll just go through that file. We'll see what changes are there and where exactly you can implement if you want to add your own custom files into it. And the end results, we are expecting the force, obviously, and we will also see the velocity and all the different contours that we have. We will also see various ways to post process your data because you have multiple ways to do that. You can do it using ParaView. You can do it using a custom Python code as well. In the case study itself, you have a custom Python code implemented. And at the end, I'll also show you another way in which you can write your own code and you can find out any data that you want using that custom Python code. And the solver used is interform. And we will also be using the volume of fluid methods within this interform solver. Okay. So first, the governing equations that we have, obviously we're solving for air and water, both of these. So for air and for basically both of the flows, you will have the Navier-Stokes equation. So you have continuity equation and momentum equation. Along with that, we will also be solving for the interface. Now, most of this Nikhil had already explained in the multiphase uh, sessions that we had. We had two sessions before that, so he's explained in detail everything about this. So over here, just to give a brief summary of whatever was taught in the previous sessions, you have this particular equation that is for your interface, and then we have alpha, that is your volume fraction. So over here, zero, we have basically alpha fraction. Your volume fraction will depend based on where exactly or your cells, how is it filled. So if your cell is filled with say fluid 1, it will behave as 1, like your volume fraction will be 1. Whereas if it is for air, then it will be 0, and if it is at the interface, it will be somewhere between these. Now, in your interface equation, in your interface solution, you will have your density changing. So that density will be based on where your volume fraction is, whether you're solving for, say, air or you're solving for the fluid itself. Okay, so your density will change based. So for that, you have this particular equation. Now coming to the schemes. So as I showed you, we have four different files. In each of them, they've used four different schemes. So you have the very first one, that is your Eulerian scheme. Then you have Crank-Nicholson. Then you have the local Euler interface. And then you have the local Euler MPLIC. Okay, so let's look at each one of them in depth. So the very first one is your Eulerian scheme. So this is the equation for the Eulerian scheme. It's a first order accurate in time scheme. Okay, it is typically used in solvers, that in transient solvers, that in which you require just a quick simulation and you don't really have to bother that much about accuracy. So I would say that it is robust and stable, but it is less accurate when it comes to tracking the interface. Okay, so you will have some interface smearing, that is because of your equation diffusion. That is, you'll have your numerical diffusion in this equation itself, as it is a first order scheme. So you will have some smearing at the interface. So in case you want to refine that interface, you could go with the second scheme, that is Crank-Nicholson. Now this is a second order accurate in time scheme. Okay. So this one will resolve your interface. It uses, so obviously you will have less smearing and your diffusion is also less, but it comes at a cost. Okay. So your computation time will increase, which in turn will which in time will increase your computational expense. So if you have a powerful system and you have time to spare, you can use this scheme. And if you want an accurate solution as well, then once if you have, now you know the very first one, that is your Eulerian scheme, and you know this particular scheme, the Crank-Nicholson scheme. So that brings us to the third one, that is your local Euler interface. Now, what this scheme does is it it's obviously a first order scheme, so it is in par with the with the Eulerian scheme itself, because the backbone is that. But what it does is that it adapts the you can say the interface, like you'll have each cell that has its own local time step based on the current number. So what this does is it will give you a refined region closer to the interface, whereas it can keep your current number, or it can solve for places where the cell is completely filled with air or water more quickly. So you will have a faster simulation with the output of Crank-Nicholson. Okay. So you have like it's a combination of both of those. It also maintains your boundness between 0 and 1. That is, it will keep it between your fluid and water. That means it is resolving your interface at high current numbers as well. It has an improved interface resolution, obviously. And it is so the downside for this is, firstly, it is a first order equation. So you won't get that much of an advantage when you're comparing to any of the higher order schemes, but it is computationally less expensive when you compare it in terms of orders. And it is slightly more complex to implement because you have all of this going on right now. So you have to implement everything properly. So the implementation part is a bit complex. That brings us to the very fourth one, to the fourth scheme, that is your local Euler MPLIC scheme. Now, MPLIC stands for Modified Piecewise Linear Interface Calculation. So in simple terms, it is similar to the previous one. So it is similar to local Euler interface, with the difference being that over here it uses a geometric VOF algorithm. So what I mean by that is, it now your reconstruction part. Okay, so where your interface is, it will reconstruct that interface using this MPLIC geometry VOF reconstruction algorithm that is placed within this scheme itself. So this will accurately capture even small details that you have. So you will have a very refined interface. So this is extremely good if you want accurate solution, and like you want to do in-depth analysis of that interface part itself. So it is good for that. This also has the local time stepping thing. So exactly what is done in the previous one, the local Eulerian interface, it does the exact same thing in terms of that. But this one is extremely expensive because you are solving for every detail. So it will be very expensive when it comes to your computational part. So you need to have a high-end system to run this, because even on my system to run this simple case, it took around half a day to just run one-fourth of the whole simulation. Okay. So you can expect it to run for at least 2 days on a typical 8-core system. So you can keep that in mind when you're running. So looking at all of these four schemes, let's see what are the advantages and disadvantages in certain parameters. So when it comes to accuracy, you would have the Eulerian, like over here, higher is better. So you would have the local Eulerian MPLIC obviously at the highest. Your local interface one will be a little bit lower compared to Crank-Nicholson. Now, this is just based on some data that I already had. So comparing those, I felt this was the accuracy graph, but it can change depending case to case. Now, in this particular case, this was the result. For Eulerian, since it's a first order equation and everything, you have quite a lower accuracy. And in terms of stability, the Eulerian case is a bit stable. Your Crank-Nicholson may fail if you do not set certain parameters correctly. And the interface, obviously, since that local Eulerian interface scheme is based on the Eulerian scheme, so stability wise, both of those schemes are stable enough. And in terms of interface tracking, the last two are obviously better because they have those advantages, as I said in the previous slides, of that local time stepping and the interface tracking more accurately. So those two are much better as compared to Eulerian and Crank-Nicholson. Now, in terms of simplicity, over here, lower is better. So you will have the Eulerian, it's more simple to set up and just run those cases. Then you have Crank-Nicholson. Your local Eulerian interface is a bit simple to set when compared to the MPLIC. And moving forward in terms of time, so how quicker your simulations are running, obviously the Eulerian ones will run faster because it's a first order scheme, and you are not resolving many things in that. Crank Nicholson again increases a bit, and as you move forward in those schemes, the time keeps increasing. As I said, the last one, the MPLIC one, that one is resolving for most of the things that you require, so it will take the most amount of time. And in terms of computational cost, again, as your time increases, your cost will also increase. So these are the results for each of those cases. Okay. And this one is just an overview. We've taken four of the major parameters, that is accuracy, stability, interface tracking, and cost. So as you see, the Eulerian one is on the lower spectrum compared to the MPLIC one. So in terms of cost and everything, it is lower, but in terms of stability, it is high when it comes to the Eulerian one. And the MPLIC is obviously in par with the Eulerian in terms of stability, but it is also having a higher accuracy, higher interface tracking, but the cost is also quite high. So since we are done with looking at the whole statistic analysis, let's go to the case itself. So as I said, once you download it, you have these particular files. So the very first thing you do is always read the README file. So let's open that first. So in the README file, it says that Crank-Nicholson, Euler, and local Euler interface, for that they have used OpenFOAM 2112. So in our case, we're just going to run it on 2412 because majority of the people will have 2412. And the local Euler MPLIC is made for OpenFOAM version 9. So that's why we've told you that in certain cases, you may require both of these cases. Sometimes you may require one over the other. So we'll run both of these in their dedicated versions that they have specified over here. The only thing is we'll run this for 2412. And then it also mentions you have some files. You have all solve that does everything. Then you have all run that only solves the it'll only solve the whole simulation part with the mesh itself. And then you have all mesh that will create your mesh. And to clean the case, you can use foam clean tutorials. This particular command changes for OpenFOAM 9, it becomes foam clean case. So let's look at that. So you can minimize this. So first, let's go with the Eulerian one. So for Eulerian, you have again zero constant system. So you can open zero. So over here, we are using a turbulence model. So what turbulence model you're using, how you've calculated each of these values. For that, you can open the report. Okay. So let's see. So in the report, you have all the governing equations, how they've computed the Reynolds number, then your turbulence length, how have they computed that, and also the turbulence kinetic energy. Those equations are also set away. So you can cross verify if you want to change any of these parameters, you can put in your values for which Reynolds number you want to run, what velocity you're running at. So all of those values you can put and you can change those values accordingly. Now, okay. So once you open the zero folder, you have alpha.water. So last time Nikhil had explained this. So let's open this one. Okay. So at the inlet, you have a fixed value, outlet, and atmosphere. So all of these. So here we have our HTL file that we've labeled it as boat. So we have set that to zero gradient. And let's open the other one. So you have K, omega, P, RGH. So let's open K. Okay. So K, as I said, they have computed a value based on that formula that they have mentioned in the report. So you can cross verify whether this value matches with the ones that they have specified over there. And over here, they've again given some boundary conditions. So you can look into detail about these. We have those documentations already on the site. So you have the open form site. So each of these boundary conditions, what they do exactly are mentioned perfectly in that document. So you can have a look at it. And at the that's like at your HTL file, you have a custom, not custom, but a particular boundary condition that is specific for these turbulence models. So you have the RQR wall function, and that particular wall function will be based on this number. And similarly, then you have omega, P, R, G, H, U, etc. So we've already gone through all of these cases in the previous tutorials, in the previous sessions also. So we'll not go too much into detail about this. Then let's go to the constant. So again, over here, since we are solving for snappy hex, as yesterday Pari said that for snappy, you would have to create a trie surface. Within trie surface, you add the HTL file that you have. Now, typically you would just have the HTL file. All these additional files wouldn't be there. Once you run snappy hex mesh, these extra files will be created. Now, bad faces is just, I don't think it's supposed to be here. By mistake, you must have left it there. But typically you would have just an HTL file and the .emesh file. Now, and this particular file will be created once you run snappy hex. It just holds your your extended mesh. Basically, when you do features mesh, all of these additional files are created. Then we have the gravitational values over here. This. Yeah. So over here is where you specify your gravitational force. So it is in the negative, he's put in the negative Z direction. So depending on the orientation of the whole block, you can see that. So let's first, I'll show you the block. So let's open this in the terminal. So let's type WSL. Then you type OF2412. Now, first we will just do block mesh to show you the mesh exactly and in which orientation it is set. We have paraform. Okay. So this is your block. And as I said, it is oriented in the YZ coordinate system. Okay, in the YZ plane. So it is that's why the gravitational field is put in the Z direction. Yeah. Okay. So now this is only the block mesh. So it's just your domain. We've not done anything to it. It's just a simple block. We haven't segregated it into air, water. We don't have the HTL file within it. So if I switch this off, like if I switch. Okay. So if let's go to volume. Okay. 1 minute. Let's do paraform again. Okay. Let's keep it this only. So if I switch to volume, okay, the volume is loading. But if you see within this block, we don't really have anything. It's just your domain. Okay. So first, let's close that. So based on that orientation, we have set the gravitational force, and then we can go to transport properties and turbulent properties. So let's open transport properties. So here is where you specify your water, air phases, basically your phases, and you specify the properties for each of them. And surface tension we've kept to 0. So these are the parameters for your fluids that you will specify over here. You have your kinematic viscosity, then dynamic viscosity, all of those parameters you can place it over here. And lastly, then we have turbulence properties. Okay. Now, turbulence properties is where over here you will change. If you want to run this simulation as a laminar case, all you have to do is change this RAS to laminar, and it will just bypass the whole block that you have set over here for RAS. It will take the simulation as laminar, and all of these files that you have put in your zero folder, it will just ignore that and it will go ahead. It will only solve for your alpha dot water, U, and P, basically your pressure and velocity. It will not take any of these parameters. Now, in this particular case, they have used the RAS model, and within that, they've used the K omega SHT model. That's why you have the K, you'll have omega, and you'll have the nu tilde. That is your nut. So for the timing, let's leave this at RAS and save. Then once you're done with all of these, you can go to the system. Again, you have your typical, you'll have snappy hex, mesh quality, surface features. So let's open, so block mesh, it's a simple block. Let's open surface features. So again, as Paris yesterday mentioned, here you will specify your HTL file. And then once you do your surface features extract command, it will run this particular whole file, and it will check your boat HTL file. Then it will check the angle that you mentioned. So how much the curves, how much you want to capture the feature edges on those curves, how much you want to capture, that will be defined by this number. So if I were to specify over here, as they've mentioned, if you specify 0, it will not capture any edges. So you'll just have a simple block. And if you set it to 180, it'll capture all the edges. So if you have a sphere, something like that, any curved surfaces, it will capture it much better if the number is higher. And then you have some base parameters, the subset features, anything you want to switch on or off, you can do that over here. You can just check from yes to no if you don't require that. Then once you're done with surface features, let's run this command. So first we've already run block mesh. We'll just run surface features. So now yesterday, Paris had shown you in 2412. Okay. So there are a few differences between this particular command, surface feature, and type tab, extract. Now in 2412, the command is surface feature extract. Whereas if you're running for OpenFOAM 9, it would be surface features. Okay. Okay, so this would be a command for OpenFOAM 9. So when we are running this case for OpenFOAM 9, you can notice this particular change in this command. Okay, so for now, we've done surface features. What this does is it will generate an e-mesh. Okay, it will first of all create all of these extended features and all. And okay, not polymesh, but in tri-surface, along with the HTL file, it would have created this .emesh file. Now this .emesh file is important because in SnappyHex, as if you remember, yesterday Paris had mentioned something in which you can automatically detect the file and in which sometimes you have to specify a file for SnappyHex to understand and to find out which curves are where. Okay, so let's open SnappyHex. So if you are using this particular feature in SnappyHex, so if you scroll down, okay, okay, they've commented out most of the part. So there is one particular feature in SnappyHex that allows you to automatically detect the HTL, or you want to use the .emesh file. So if you're using that .emesh file, you have to have that. So for that, you're using the surface features. Otherwise, SnappyHex will automatically detect the geometry and will start to snap based on that automation that it already has. So in this case, we are not really specifying that, but ideally you would specify. Okay, so in the features part, they have commented it out. So over here you would have boat, and then over here you can detect that image file. So it will read that image file, all the data that it has captured within that image file, and then it will create your mesh accordingly. So let's keep that aside for now. Let's see the Snappy Hex itself. So at the start, we are using castellated snap, and but we're not adding layers. So for that, you have changed it to false. Then coming to the geometry, you have obviously a boat HTML file. So over here, you specify the file that you have and the name. And over here, they've also given the type that they want. So they've kept it as a wall. So it'll just behave as a simple wall. And then you have a refinement box. So you have refinement box 1 and refinement box 2. So they specified the coordinate system. How do you specify this coordinate system? In the previous sessions, they have explained this. So we'll not go too much into detail. It's basic that you specify the lower limit and the higher limit of your box. Same goes for box 2. Once we do the meshing, I'll show you the refinement regions as well. Then you have your castellated mesh control. In this, you will specify how much cells you want. So your max local cells, max global cells, how much refinement cells you require. Over here, the minimum refinement cells. So here they've set it to 0, and the cells between levels. So if you are changing from a level 1 to level 3, how many cells in between of those you will require. So it is not a drastic change. So that you can specify over here. Then features, again, over here, you'll specify your emesh file. In our case, we are not doing that.
Excuse me, can you increase little bit font size?
Okay, 1 minute. Okay, is it visible now?
Yeah, yes.
Okay, yeah. Then we have the resolve feature angle. Here they've set it to 45. You can again lower or increase this number. You can see then what happens when you do that. How much faces and how much curves it is capturing. And over here, then you specify distance and all region-wise refinement. They've just switched all of that off. So refinement region over here, they've specified the levels. It's 1 and here it's 2. So you can change that. Again, location in mesh. Yesterday, Paris had very nicely explained this, that your this location in mesh point has to be exactly inside a cell within your domain. It does not have to intersect with any of the lines or any of the points that are there within your whole domain. Otherwise, it may throw an error. So you can check that as well. He had also explained how to find that particular point using that one filter in ParaView. So you can check that as well. Allow freestanding, yes, we've kept that. Snap controls, again, they've changed this. Now over your tolerance, how much tolerance you have for that snapping feature. So here they've set it to 1. If you have a good enough case, then you can set it to 1. If you have a medium mesh in which you're not really sure whether it is good enough or not, you can set this value to 2. And if you have a really coarse mesh, you can change it anything above 2 is fine. And your solver iterations, how many iterations it will take to snap. So those iterations are set to 300 relaxation. Now add layers, since we're not really doing anything, we've set it to false. So it will not create or it will not add any layers over here. So that is set to false. So any of these features will not be uh, X will not be added to the whole geometry mesh itself. Feature angle, all of these features are there. And then at the bottom, we have mesh control or your mesh quality. This will basically just check whether your skewness is within this range, internal skewness, all of these things Paris has already explained last time. So we'll not go too much into detail about this. So let's close this. And then we have the set fields dict. So in this, you are basically setting which particular parts are your air and which one is water. So all of those things are set within this. So you have box to cell, box to face. So anything that is within this cell, you are specifying it as water. So you've specified alpha water 1. So 1 means that it is filled with a particular fluid. Now in our case, we have set it to water. So anything within this particular box will be water. And anything outside this box, we have default field value set to alpha dot water 0, that is air. So in this way, you can specify which parts you want as water, which parts you want as air. If you have multiple fluids, like if we had water, oil, and air, so you can change all of these. You can specify certain zones or certain areas in your whole domain as whatever that fluid is. Now, Nikhil had already shown that as well. He had done a dam break case in which we had 4 different fluids. So you can check that. It was day before yesterday. So you can check those recordings as well. So once you're done with set fields, you have refine mesh. We'll not go too much into that because there is a particular um, thing while running these cases. So you have to switch off some of these parameters for it to properly run. Because in the past, there were a few people who were complaining about the case not running. So I'll try to resolve that as well. And then we have our basic block mesh, control decompose, FE schemes, FE solution. So first we'll go to the FE schemes since we are changing schemes over here. So you see the schemes that we're using over here. The default one is Euler, and you have set some parameters for that accordingly. Now in the different files that we have, so you will have Euler, Crank-Nicholson, local Euler, depending on which one you're using, MPLS, your interface. So all of those will be changed over here. Okay, so your FE schemes. So you're trying to compare the interface tracking for all these 4 schemes as well. And lastly, we have a decompose. Now this particular decompose is set to 80 subdomains. Now on a typical system, you won't have 80. So we'll change this to we'll change it to 4. Okay, because my system has 6 cores. So again, we've shown this in previous sessions also. We'll just have a quick look at that, how to find out how much cores you have on your particular system. So you can do that using the LS CPU. Okay. Now now you can do 2 things. Is you can either run each of these commands manually. So we know that we're using snappy hex. So we can first do block mesh, then you do surface features, then you can do snappy hex overwrite. And after that, then you can run your solver itself. If you want, you can decompose it as well. You can use decompose par. So you can do all of these manually, or you have the all run case. Okay. Now in that previous README file, if you remember, they had specified that you will have an all solve, all run, and all mesh. Here we have also an all plot file. So in the all solve, as they said, that you will have it to do everything. So all solve is just running all mesh and all run. Okay. So let's look at all mesh first. So now if you're planning to run anything using the script, always check how much files or not files, how many domains they have set this to, because now obviously 80 would throw an error. So let's change this to 4 and let's change this to 4 as well. Okay. Now the redistribution part, you can comment it out because we're not really going to do that much with the redistribution part. And in the other solvers, it may give you an error as well. So let's keep this as commented. So we're just running. So say if we have alpha.water, like if you run this case, it will create an alpha.water. That's why we've labeled it as alpha.water.org, because Nikhil must have already told you this, that when you are running when you're running any multi-phase case, if you have water or any of these files, it will overwrite this file with the data that it is currently calculating. So it's always beneficial to keep this alpha.water as an original file. So if you want to make any changes, you will have that original file. Otherwise, you will have just an overwritten file. So what we're doing is we are deleting, if in case there is an alpha.water file, we are deleting that. So this is what this command is doing, rm. Then cp is just copying the original file to alpha.water. Okay. After this, now for the meshing part, these 2 commands are not that important, but when you're running a simulation, these 2 will be extremely important. And then we are just doing a foam clean case. Again, if in case we have any old files, it will just clean those. It will make a 0 directory. Now, this particular 0 directory is for snappy hex, because snappy will create its own cells and all of those things, and it loads everything within that 0. So what we'll do is we'll try to run it manually for now for the meshing. So the very first thing we'll do is we will change this 0 to 0.org. Means we'll keep our original 0 file separately. We don't want anything overwriting it. You never know that if something will overwrite it or not. So let's keep 0 as 0.org. So within this, we have all of our original files, and we'll make a copy of this and we'll place it here. Okay, so we have a copy. We'll label this as 0. So if any changes happens also, we at least have the original file. Okay, it's a good habit to always do this, because if you have any files that are overwritten, you have some files to look back at. So let's delete this. Okay. So we have now our 0 file, the copied one. And now we'll just do our meshing. So like if you're doing snappy hex, you will first do block mesh. So first let's clean the case, home clean tutorials. Okay. So first let's do block mesh. Then we do surface features, extract. Okay. Now once we've extracted all the edges and everything, you can do snappy hex mesh dot dash override. Okay. So your override command is in simple terms just overwriting any previous data that it has, and it tries to interpolate the points that you have with your HTML file and the block mesh itself. So it's just trying to merge your block mesh and your HTML file together to create one uniform and unified mesh. So your snappy hex will take a little bit of time. Max it takes like around 1 minute. So let's wait for some time while this meshing is done. Okay. Okay, so now it is doing the snapping iteration. So you see we set the iteration to 300. So after 300, then it completes that. Okay. So it will be done now. Yeah. So once it is done, we'll just see the mesh itself. Okay. So you see previously we just had the block, the domain. But now if you see on the left-hand side, we have this patch boat as well. So I'll switch off the internal field. We'll only keep the boat. So this is our mesh for the ship itself. Okay. Let's keep that surface. So I'll switch on the internal patch. And we'll take a slice to show the mesh. Okay, let's take this one, apply, and we'll switch on surface with it. Okay, so you see we had specified the refinement box. So we've had a refinement box over here and the second one closer to the geometry itself. Okay, so we can switch on the show plane and triangulate. Okay, we have here. Okay. So this is your mesh. So we will have the interface also somewhere around here only. That's why we've refined the whole region around this place to have a much more refined interface tracking. So this is about the mesh. So now let's run the simulation. Okay. So for this, we have the all run. Okay. Let's open this. Now your all run, as I said, if you have any alpha.water previously, it will just delete that. And then we will copy the original file. Now, since we ran a case for Snappy Hex on a single core, so we don't have any of those processor files. If you are running it in parallel, like if you were to run the all mesh file, the all mesh would have decomposed your domain. Yeah, over here it would have decomposed. So let's keep this open. It would have decomposed your domain and then ran it in parallel. This is what the command would have done, and then it would reconstruct the mesh. Okay, so it will run a bit faster. For the second case, we will run it in parallel. So I'll show you that as well. So, okay, all right. So what this is doing is it is just going to clear all of those processing folders because we want to run this case in parallel. Then if we have any post-processing file or something like that created, it will delete that as well. Now, the second thing we will do is set fields because we have to differentiate between air and water. So set fields will run that. And then we will again redistribute your whole thing. For that, or you can either do decompose like that, or you can just uncomment this part and comment this one. So we'll keep this because when you're running any of the Crank Nicholson or any of those particular cases, now in Eulerian, these particular commands run fine. But in your Crank Nicholson, the local cases, it gives an error. Okay. It won't give an error, but it just gets stuck at finalizing parallel and all that thing. So for those kind of to avoid that error, we are just doing a simple decompose and we don't really need the renumber mesh. These particular commands are just so that your solver runs a bit more efficiently. If you just decompose it and then run it in parallel, sometimes it may take some more time, or it will take obviously these cases will take time because they are multi-phase case and you are running multiple things at one time. But there are multiple ways in which you can speed up that process. Like you have hyperthreading and all of those. Like if you open one of these files, there is a particular command for that as well. So we can, for now, we'll just comment this out. We'll just do a simple decompose and we will just do simple parallel running and a simple reconstruction. So we'll keep this and we'll comment out these. Okay. Again, we'll change this to 4 because we only have 4 cores. Yeah. And speaking about cores, if you want to find out how many cores you have, you can again do ls CPU and you can scroll on top to cores per socket, that is 6, and sockets you have 1. So you have just 1 socket. So in total, we have 6 cores. So I can use a max of 6 subdomains. Okay. Yep. So we change this to 4. So now we'll use this particular file only to run the case. Yeah. And one more thing. Now when we are running the MPI run, if you notice that in previous cases when we were running it in parallel, we were just doing up to here. MPI run NP, that you're specifying number of processors, 4, and then your solver name and parallel. But over here we have added an extra line or an extra command that is log. Okay. So if you just type this particular command and you run your simulation in your terminal, it will just run everything in the background. Okay. So it will just blink your cursor over here and it will show running in parallel, and you may think that it is not running something, but in the back end it is running. So I'll show you how to see that back end also running. So let's run this particular command first. So the command said that we have to do set fields. Before that, we'll go to the 0.org. Okay. Okay. So see, for like these reasons, you should always have the original file. Now it's not allowing me to, okay, deleted that. Fine. So let's copy this particular file, copy paste, and we'll keep this as 0. Okay. Now you can delete all these zone identifiers. And let's change this 0. Before this, we'll just copy this, copy, and we'll change this to alpha.water. Yes. Okay. So now we have our alpha.water and we have the original files as well in our 0 folder. So as per the sheet, we had to change that alpha.water. We don't have any processes, so we're not deleting any of those. We'll do set fields, decompose, and then we'll run it in parallel. So you can do set fields. Okay. It has differentiated your domain, so you can see that. Okay. So we have now this is our domain, and now you can differentiate between patch atmosphere, patch bottom. Okay. Okay. Once you run the simulation, you'll be able to see it properly. Let's do that as well. So we'll do decompose. Now we've set to 4, so it will decompose it into 4 subdomains. And if you do MPI run dash NP 4, number of processes 4, interform, and then you run it in parallel. Okay. And as per that command, you want to log. Okay. So let's cross verify. Okay, the command is different over here. So we want to log this particular file. Okay. Okay, parallel log. So if I run this, now you see it is just blinking my cursor over here. So sometimes for people who run this command the very first time, they might think that nothing is happening or my terminal is hanged or something like that. But if you see, now if I refresh it, you have processor as well, and you will have this log file. Okay. So it is logging everything that happens in the terminal into this particular file. Okay. Now this is good if you are planning to post process something or you want to check your residuals after you run your simulation. So for those kind of cases, it is good to log your files so that you have this data and you can plot it later on. So this will keep refreshing every time. Now, in case you want to check it on the terminal itself, okay. So I can just open CS new part of the terminal, type WSL OF2412. Let's go to the path that we are running our case in. So we'll go to run. Let's do ls. So we're using the multi-phase ship case. So let's do cd multi-phase. Again, we'll do ls. We have cd multi-phase. Again, we'll tap ls. Ls will just list everything that is there within that particular folder. And now within this, we want to go. Okay. So ls over here is happening. Yeah. So you can clear this whole thing. Let's clear this. Now, if you want to, like you want to tail or you want to find out exactly what is happening in this particular file continuously. So you can use tail dash F and then you can type your file name. Okay. So if I do this, it will start tailing that what is happening in that particular file. You can check it in real time. So you can check whether any of your solutions by looking at the, like you can read the terminal and you might know at that moment that your solution may diverge or it is converging properly or the results that you're getting are fine or not. Now in our case, it is giving you the forces. So you can check the total force, like you have the total forces, then you have pressure, viscosity, and all of those things. So you can check these parameters whether they are aligning with something you're trying to validate or it's at least close. So this helps in when you are not sure whether the parameters that you set are correct or not. Then at that moment, you can just switch off your simulation and you can then start a new one. Because sometimes it may happen that you have done your whole simulation and then you realize that you forgot to place that one particular parameter and now you have to again rerun the whole case, so that much time has got wasted. So for those kind of cases, it's always good to check all of your these parameters that you are trying to find whether they are accurate enough or not. Now this particular terminal, you can just press Ctrl C and terminate it, and it will not terminate your original case. So in the background, this is still running. So you have this benefit as well of using the log command and trailing it in the other secondary terminal that you have. Okay, so if you are running the simulation using this particular file, you will have it display something like this. Okay, so don't think that it is not working or something like that. It is running in the background. Just make a note that it is showing a log file and whether that log file is getting updated or not. So first it was 7 KBs, now it is 82. So it is writing some data inside it. Now, this particular case, we already have it run. So we'll stop this, just press Control C. So I'll show you the run results. So we have for Euler, let's open this. Listen, F2412. So here we have, here instead of pressure, we click alpha dot water. Okay. Let's click on this one. I'll drop down the opacity and enable that boat patch. Okay. Let's switch to 2D. Your multi-phase case. Now over here you have the fluid, here you have your air and the interface over here. So now we'll try to compare whether what advantages and disadvantages I said, like interface tracking for oiler is not that great and all. We'll try to compare that. Okay. So we'll keep this, we'll increase the opacity. Okay. We'll load all of these side by side and we'll see that. So for now, we only have the oiler case run. So if you want to post process the data, like how in the report it was, there are multiple ways. You can use a slice and you can define your plane Z. You can move it up or down, change to 3D. And let's say we want it at, instead of, want it a little bit at this range. Apply. Okay. And instead of P, we want to see the velocity. Now this is for air, whereas if you want to see the velocity of the fluid itself, we'll lower this a bit. Line. Yeah. So if you run the simulation for a longer duration, you will see all of those contours that are there in the report. Now in our case, we've just run it for a short time, so we are not able to see that much of it. So this way you can post process. You can use a slice or you can use clip. So there are multiple ways to do that. You can even load the boat separately. Like if I click on open, we have this small window. So I know that my HTL file is within the constant try surface. So I can load this boat HTL. So this way I can keep my boat. So we'll switch off from the main file, the boat, apply. Okay. So for this, you'll have to load it separately and keep the opacity of the whole domain also less. So this way you can load your HTL file. You can see how exactly the contours are there. So if you want to visualize any of these, you can do these particular ways. Now this was for Euler case. Okay. Let's close this terminal. Yeah. Now we'll run the same thing for Crank-Nicholson. Again, the procedure is the same. There's nothing different as such. You only have to make a few changes over here while running for these cases. So I'll show you the key differences that we have between Euler-in and all the other cases. So you'll have firstly the scheme change. So over here we are specifying the default Crank-Nicholson 0.7. So over here we've changed the scheme. Along with that, you have to change your decomposed power, because in each of these cases it is set to 80. So we don't really have 80 cores, so we'll set everything to 4. And this time I will run the case in parallel for Snappy Hex, so that way you will see those files generated. Now for all mesh, you'll open this, set this also to 40, this also to 40. We'll keep everything as default. And we'll change all run. We'll change. Now we don't really require this particular decompose. Okay, for now, I'll show you what exactly is the error that you get. So we'll leave this to 4, everything to 4. Okay. So for now, we've just left everything at default. We will close this terminal, close all. Okay. So now let's open in terminal. Okay. So first we will just do foam clean case tutorial. Okay. And we will first run bash all mesh. Okay. So all mesh will first run your surface features then it will run your block mesh, then it is going to run your snappy hex override. Before that, it will decompose everything. So it decomposed and now it is running in parallel. So while it is running in parallel, I can show you. If I see, so okay. So in parallel, we have decomposed the whole domain into 4 subdomains and we're running on each of those processes. So the meshing will be a little bit quicker as compared to last time. Last time it took a little bit over 2 minutes. This time it will be a bit quicker. So you see over here, it will create the mesh and then once it is done, it will reconstruct it. Now in a 0, we have created that alpha.water because in the script itself, it has set that it was set that way. So you have all mesh, it will create that alpha.water and it will clear any old ones which were there. It created that 0 dict also. Yeah. It's on the snapping part. Now, when we are running the all run, it will first delete all of those processor files. If any post-processing file was, that will delete that as well. And then it will basically decompose the whole domain and I can run the whole thing for the simulation this time. Okay, so now it is done. So now let's run bash all run. Okay, so it first will clear all of those files. It will clear that and it will again make everything. It will decompose. It is running set fields now. And now it was running the decomposition part. Okay, so if we, yeah, so it decomposed the domain, but now it is stuck at this part only, finalizing parallel run. And it keeps getting stuck at this only. It does not do anything more. So to avoid any of these errors, you can just stop this. And over here, you can just do a simple decomposition. So you can comment this one out and you can enable this one. Same goes for renumbering. Okay.
Even just I'm interfering because
ma'am.
this online attendance form has been given.
Sure, ma'am.
So maybe we can take 30 seconds or maybe 1 minute break and so that they can mark themselves present. So
Yes, ma'am.
participants, please fill up the online attendance form and then we can continue.
Okay, so once done, Paris, can you let me know?
Sure, sir.
Yeah.
We can start, sir.
Okay.
There are 15 completion thumbs up I can see. We can start.
Okay. So once we've made the changes, like you can comment out the redistribution part, renumber part, and you can keep the normal decompose and normal reconstruct. So once we do that, we'll just run all run because it already has the form clean and everything inside it. So now it is decomposing. It decomposed the mesh and then it is running in the background. So again, we can check that using the WSL OF 2412 and we'll go to that particular file path. Yeah. So here we have, not Euler, sorry. This time we're running the Crank Nicholson, right? So we can do tail dash f log. Okay. So you can see over here it is running in the background. You can cross check it with the log file that it creates. Okay. So in this way, you can make the necessary changes to the other files as well to avoid any of those errors that pop up. Okay. So let's stop this one. Now this particular case also we have it already run. I'll just show you the next changes for interface because the MPLIC one is made for OpenFOAM 9. Okay. So yeah, for the interface one, again, changes are first you will check in your FE schemes. Over here we have local Euler and okay. And you can then make the changes in your decompose power. Now in this case, it is set to 6. If you have 6 cores, then it's fine. So you can change this, and in the all run, you can in your all mesh, you can change that particular parameter for decomposition and in the all run as well. Okay. Now you also have this additional file named all plot. Let's talk about that a bit. So in all plot, we are just plotting that force that we require. Okay. We're trying to find out the force acting on the hull itself, right? So we are using this Python code for doing that. So, so in this particular file, you have the Python code itself. So you have it, it is just a basic Python code. It's just reading the post process file of forces like over here. I'll show you the run case because we have that over there. Okay, I can't really go on top. Yeah. So we have, let's see the Euler case only. We have this run. So we have this post processing. Okay. So when you are running, you'll have post processing forces under 0 and you'll have multiple, you don't have multiple, but you'll have a few files. Okay. So you have this force file. So you can open the DAT file. Yes, good. Okay, so over here it is logging all of those things. Like when you're running it on your terminal, as you saw, it was showing you the total force, that was showing pressure, it was showing viscous. So all of these force in their XYZ coordinate system is saved over here. Now we just have to extract this particular data and present it, or at least put it into a formula for computing the force part in a graphical representation, right? So for this reason, you can do this using the Python code itself. Now that is provided over here. So you have this plot. So what that is doing is under post processing, under force, under 0. Now they have added that run sh. So under that run sh, it is just trying to find that. So that run sh is over here also. It's kept out there. So that run sh is again opening the post processing force 0 force DAT. Now over here they have complicated it a bit by adding multiple files into a file that are sourcing the exact same thing. So you can modify this, you can write your own custom code. So we still have half an hour, so I'll be able to show you that Python code as well. So for now, you can run this particular file. So let's do that. So let's open this in terminal. WSL OF2412. And if you want to plot anything, you can plot that Python code itself. You can just type Python 3 and then you can type the file name. The file name was plot.py. Okay. You can just type enter. Now over here it has generated this file. Okay. So you can close it directly or you can first terminate it from here and again press terminate and then you can delete close this file. Okay. So you okay. So you just hit it multiple times, it will terminate that operation. Or you can also do bash all plot. Okay, so it does the exact same thing, but here it is just a bit automated. So you don't have to run multiple commands. Okay, so again, you just yeah, so it terminates that. So you can just do Control C to terminate the whole operation. So this is one way to plot your data. Okay, now I showed you for the first three, Euler, Crank-Nicholson, and local interface. So let's see the MPLIC one. Now that is made for OpenFOAM 9. Okay, I have the case over here though. Okay, this is for run case. So this is the run case that I have. I did not run it for the entire time step. Like it was ending at, you can open the control dict. So you see, it is ending. Now I've changed it to 500, but ideally it was set to 10,000. So obviously 10,000 will take a lot. Like to just run 500 iterations on 7 cores, it took about half a day. So you can expect this to be computationally very expensive. Now, if you have a high-end system or you have a cluster system, you can run this a bit quicker. And also for for the post-processing part, okay. Now, in this particular file, like if you see the run file, in post-processing, now this particular file isn't just directly created like that. Okay, you need to add a particular function that during your simulation, it will try to compute things based on that. So where do you specify this function? Like now we want to compute the force. So we need to specify a force function that will be computed when your simulation is running. So that force function is added in your control dict. If you scroll down after your runtime modifiable, you will have this additional tab known as functions. Within this, you can specify your force block. Now your force block over here, what it is doing is it is first of all computing your forces. So it is directing it towards that lib force file. So it is trying to find that library for forces. In that all the formulas are there. Which patch you are using. So it is going to compute the force on the boat patch. Okay. Now, if you have like flow over a cylinder and you want to find out the drag of that cylinder and all, if you have like cylinders in tandem or you have multiple cylinders and you want to find out the drag for each of them. So for those kind of cases, you would have to differentiate out all those patches. You can't just label them under cylinder, because what this does is like now if I had a boat and behind this I had another boat in a tandem configuration and I wanted to find out the drag of the second boat. So I would have to label the patches separately. Okay, so I would have to label it as boat 1 and boat 2. If I put both of them together, OpenFOAM, what it does is it will combine the area of both those patches together and it will give you the output. So that if you're computing for boat 1, it will give you the same results. If you're computing for boat 2, it will give you the same result. It will not differentiate. Whereas the drag for the second boat should be lesser compared to the first one. So if you're running multiple patches and you're doing some multiple simulations on different geometries, make sure you segregate those patches out separately. Okay, otherwise you might get the same results for all of them. And then rho infinity. Now here you're specifying your viscous and all of those parameters for water. So accordingly, they have changed it. You wanted to log the files. So during the time, during your simulation itself, it in your terminal or when you're running a simulation, it will log those files. Either ways, it is going to log it into that particular file. If you want to just check while the simulation is running, you can switch this on or off if you don't want to see it. Right control is your time step, and this is your coefficient of rotation and all that. So over here, you don't need, usually we set it to 0. Over here, they set it to 0.01. So you can check all of those things. Okay. Now, if you want to find this particular block, you can go to, let's open a new one. Let's go to Ubuntu. And now if you are, again, OpenFOAM 9 is in OPT. So let's go to OpenFOAM 9, OpenFOAM 9, and let's go to the applications, or again, you can check an application utility and post process. Okay, these are for creating those. If you want, you could do that file search. So you can open this particular thing in terminal and you can just do grep. Okay, first you have to go into WSL. OF9 grep dash R, and then just let's type force. Okay, so now it has given me so many searches for just force. So then you can open one of these tutorials and you can copy paste that particular block that you want. So it is saying that, see, in mesh, in control dict, include force coefficients is there. So if I want to find anything with force or force coefficients, I can copy in these particular blocks. So let's go to tutorials, mesh, snappy hex mesh. Okay. So in tutorials, under mesh, under snappy hex mesh, under motorbike. Okay, so wait, let's see the terminal again. Okay, so under motorbike system, snappy hex mesh, motorbike system control dict. Snappy hex mesh, motorbike is a file though. Let's check another one. The tutorials compressible RAS Naka. Yeah, this one is there, fine. Let's go to compressible. This one is for row simple foam. Row simple foam, Naka airfoil system, check in control dict. Okay, here we have one. So over here functions, they have used force functions and all of those. Now here they've just included as a function. So you can check the included files. So over here they mentioned force files. So over here they are checking the force coefficient. So you can again copy these particular blocks into the file that you require. Like in our case over here. And then you can change the patches based on the patch name that you have or you're trying to compute it. So you can find out your force coefficient, forces, if you have some wall shear stress, all of those parameters are there. So you can post process all of that using a custom Python code. But if you're using a Python code, they have to be first enabled over here. So only then OpenFOAM will save a file with all of that data. Okay, so you can do that this way. So let's look at the file that we have to see. So the MPLIC. Now this one is set for OpenFOAM 9. Again, you can open the system. You can open, not control dict, FV schemes. FV schemes, then here, see, we're using the local. But over here, if you scroll down, we have the Gauss, means which div scheme we're using. The schemes that we're using under that, we have changed it to MPLIC. Okay, so these changes are there in the FE schemes. Okay, so for now, let's just try to compare the results. Okay, let's see whether that interface tracking is good enough or not. So for each of these files, I'll first create a .foam file. It will make it a bit easier rather than opening them in multiple terminals. So this one is for OpenFOAM 9, and we'll just do touch results.foam. Okay, so let's close all of these. Okay, so over here we do. Okay, so we do have a results.foam, and okay. I can't see the top. Okay, hide video panel. Okay, fine. Yeah. So MPLIC is done. For interface, we do have a .foam file. Okay. For Euler, we'll create one. WSL. Touch results.foam. Okay, and let's go to Crank Nicholson. Again, we'll do touch results.foam. Okay. Okay. Can somebody just confirm whether my screen is still sharing?
Yes.
Okay, okay. Yeah. So we've created these .foam files for each of them. So we'll just open Paravi for one of these. Let's open for Euler. Two for 1, 2. And then we will just do parafoam. Okay. Click on apply. Right. Okay. So we have this particular case. So this is for Euler. Let's open one. Okay. Before that, we'll split this into render view. And for this particular file, we'll open Control O. And instead of Euler, we'll go to Crank Nicholson. And we'll open the .foam file. Apply. Yeah. We have this one. Instead of pressure, we'll change this to alpha.water. Go to the last. This one we will also orient it this way. Alpha.water. Last. And let's split each of these. Okay. You can. Okay, you can't really drag it over here. Okay, here this one. So for this particular one, we will set it to the local Euler interface one. So for the interface one, we'll save this one. Okay, let's orient this one. And we'll change this also to alpha.water. And over here, we will change this to the MPLIC case. Apply. Yeah. So we'll change this to alpha.water. Let's go to the last one. Okay, now this one hasn't converged completely and the simulation wasn't completed. So it's giving some disturbance. Okay. We'll take a slice for each of these because the mesh is a bit refined when it comes to X normal. Yeah. We'll change this to alpha.water. This one was for this. Okay, so let's change input. The slice to interface one. Okay, so this slice is for interface. This one, we'll add a slice. Okay, so this one is a bit distorted. And this is for the second case that we have. Add a slice for that. Okay. Switch to this one. Slice, apply, change to alpha.water. Okay. And finally, this case. Delete this one. Oh, yeah. Okay, we'll open this again. Sorry about that. This is the oilier case. Result is .4. Yeah. And we'll take a slice for this particular case. Okay. Let's zoom in. So this is for oiler. Let's show plane. This one also show plane. For this one also close the show plane for all. Mhm. Mm. Okay. Yeah. So you can see the diffusion, the numerical diffusion that we have. This one, do not take a slice. Okay. This. Delete the slice. For this one, we'll take a slice. Yeah. Alpha dot water into this one. Yeah. Mhm. Okay, my bad. Okay, understood. And then we have this one. It's a bit distorted, so we can't really see that much. So the Eulerian one, if you compare just the Eulerian and the Crank-Nicholson, so you see the difference between the order. Like as I said, the very first one is first order, this one is second order, and this one is also it's based on the Eulerian, both of these, but it's just that we are changing some of the, like it has the local time step capability. So this one is a bit smeared compared to the Crank Nicholson. The Crank Nicholson is much more refined. Now, this one, if we were to run the whole case, this one in theory should be much more clearer than compared to all of these. But again, due to the time limitation of the whole thing, we can't really run that case. But fine. So this is just a basic comparison that they've done. Like if you check the report also, scroll back out. Here they've compared the residuals for interface, that is your local case, local Euler, and the MPLIC one and the Crank-Nicholson one. So you can have a read of this file as well. And over here, they have done a result comparison, forces plot. So how does the force change, or at least when you're running these cases, how does it affect based on these particular uh, schemes? So for Euler scheme, you can see the case, and for Crank-Nicholson is in blue and the expected results. So based on these schemes, which one is good over another and for what types of cases you need to run those, you can see that. Now, as I said that Dr. Prabhu had also submitted one research migration. So you can check that research migration under research migration tab. You scroll down to completed research migrations and you can scroll down to, okay, see here. So at case study 26, so this particular case of his is also there. You can read this, you can download it. This is also on hull resistance only. So you can check this out. How is it different from the one that I demonstrated, and which schemes he's using, and why those schemes are better off than the current scheme that we are using in all of these multi-phase simulations. So you can do your own comparison. So if you are into, say, the shipping industry and you want to find out which particular ship hull design and how much resistance it is causing, so for those kind of simulations, you can do your own study, and based on that, you can again compare schemes, you can compare different methods that you have, different geometries as well. So that can be done in open form as well. And coming to the Python code, now the one that you saw was a bit simple. So you have a very basic, you're just copy pasting the whole thing, and you're just finding out your coefficient of drag, your not coefficient, but the drag force and all those other parameters. But in case you wanted to find out, say, straw hole number, or your at least coefficient of drag or coefficient of lift, so you can write a custom code like this as well. Like over here, you can see that we have mentioned the length and the your characteristic length and your velocity, because in straw hole calculation, those are important. But if you just want to find out coefficient of drag, coefficient of lift, you can add those formulas as well. It's a simple formula. So you can add those, you can see the fluctuations, and then once you plot it, it will give you a nice graphical representation of your data. So if you want to find out CDCL, like for an airfoil case, you need to find that out. So you can run your own custom Python code. So see, the limitation in post-processing is not restricted to only coding in Python. Like most of the people might not know Python. So for them, ParaView is there. You can use the calculator feature. So in ParaView itself, on the left-hand side, if you click any of these, you have this calculator feature on the top left. So over here, you can select a particular data. You can select a particular data set, and you can add your own custom formula for it. And it will plot your whole graph for that. And then you can export that particular result, as I think Manzil had shown here, that you can remove the CSV data for that. So you can plot that out as well. So there's no limitation when it comes to post processing or how to visualize your result. In ParaView is overall capable for doing that. You can see all of those things. Okay. So yeah, that brings an end to this whole case and the simulation and the demonstration part. So if there are any questions, we can take those questions now. Okay, so 1 minute. Hello?
Sir, you are audible.
Okay. Because I can't see my Zoom tab. I don't know where exactly did the app go.
You can try pressing escape.
Okay. Yeah, it's come, it's come. Thank you.
No problems.
Okay. Okay.
Sir, there was a question
Mhm.
regarding when to use the zero gradient parameter.
Zero gradient parameter, right?
Hmm.
Okay.
In the
So
boundary.
in terms of velocity, if you are using zero gradient, you would typically use it for far field conditions. So basically zero gradient, what it does is it just takes the very last cell that you have and it just applies that to that boundary condition. So whatever is happening in that very last cell of yours, it will apply that as the boundary condition. So you can say it is adapting based on how your simulation is going ahead. Whereas the fixed, any of those fixed values that you have, those are like hard coded, or you're fixed those values. So your cell cannot do anything else besides running that particular boundary condition that you applied. So that is when you will use zero gradient, when you are just trying to simulate some far field condition, or you just want to, like, that's why we use it at, usually at simple cases we use it at the outlet. In far field condition we use it at top and bottom if you want an open channel or an open simulation. It's not constricted by walls or anything. So for those types of simulations, you can use zero gradient. Okay.
So there is a question in the chat box.
Yeah. Okay. So the all mesh section topo set present any requirement. Okay. So 1 minute. I'll just check that. I may have missed that out. Wait. In all mesh section, could you specify plugin in which particular case? It will help me find that out faster. Euler case, no? Okay, wait. All mesh topo set. Okay. Yeah. So see the commented out sections now usually. Yeah.
Even can you share your screen, please? Thank you.
No, I was just saying it's commented out. I can share it as well, not a problem. Yeah. So I was saying in this particular case, you have a few commands that are commented out, like toposet, refine mesh, all of those. Now for toposet, I'm not sure. Wait 1 minute. Is the file there? Yeah, toposet is not there in the system file. So your toposet is just you are defining a set of cells to behave in a particular way, like you are segregating that out. So you can give conditions like if you are running a CHT case, that is when your toposet and all those files will come into play because you have your domain, and within that particular domain you are specifying a set of cells to behave like a solid or another material. But in our case, we only have the HTL file and we have already segregated out air and water using set fields. So toposet is not really required. Now this case is a bit old, so you might find some older, like whenever we are submitting the newer cases, if you see, we try to tell the interns not to type or leave any of the previous commands that they are not using, because it creates a bit of a confusion to a person who's just trying to run a case. So now like how you said that will you be requiring toposet or not? Now in this case you don't need toposet, so you can just bypass all of that. Okay, hope that answers the question. Okay, so when running, it is running fine, but when coupling with different governing equations, it's not clear. So what exactly in the governing equation it is not cleared? Okay. Because see, your schemes, like if you're just trying to run something by changing a scheme or sometimes, so in that FV schemes, you have multiple parameters. So you have to check your DDT schemes, you have to check your div schemes. So all of those have to match. Again, those everything in that particular file is mentioned on the OpenFOAM documentation that you have. So which particular schemes are present in your OpenFOAM 2412 and OpenFOAM 9. So those things are already mentioned, which ones you can use. So how exactly should we couple the RANS equation with the other governing equations in the model? Okay, so wait, I'll share my screen. Okay. So RANS and all of those, like if you're trying to implement turbulence modeling in your constant, you have the turbulence properties. Okay. Okay. So now when you type RAS, it is just it's not that you are coupling anything separately. It is already pre-built and fed into OpenFOAM. So when you just type this keyword, it knows that RAS is your Reynolds average Navier-Stokes equation, thing. So you have to run that whole thing. So it OpenFOAM knows which particular model. So over here you can run RAS, you can run laminar, you can run LES also. So again, when you type RAS in this block, you have to specify which particular RAS model. Now in RAS itself, you have K omega, you have K epsilon, you have various differences. You have K omega SHT as well. So all of those schemes, you have to mention which particular model it wants to solve. Because if you open the back end, like I can show you, that's okay. Okay. So let's go to the back end. If you want to see in tutorials, OpenFOAM 9, let's see. I don't exactly remember whether it was in applications. Let's see, utilities under post processing. No. For turbulence modeling, there is one particular place where they store all that data and you can open that. I think it was in SRC. Okay. This is momentum transport. Under SRC only it was. Let's check. This is OpenFOAM's original files. So you can check under OpenFOAM, like under the OpenFOAM thing, instead of tutorials, there are multiple files. Within one of those, it specifies exactly how that model is running and which particular models are present in OpenFOAM. So if you type LES and you're using any of the LES models, if you're typing RS and using any of the RS models, those equations are already present in OpenFOAM. Now, if you want to change any of them, if you want to introduce anything custom, you can make your own libraries as well. And you have the GitHub repositories also. They also have a few pre-built custom libraries you can compile. They usually give the instruction sheets of how to compile a library as well. So you can have a look at that as well if you're trying to do something custom or you're wondering how exactly is the turbulence modeling linked with OpenFOAM. So you can check all of these backend files because everything is there within this and everything is in C, C++. So if you know C, C++, it is really simple. And the equations also are not entered in a very difficult way. You can always open that. So even if you're looking at it at the first time, you will know, if you have seen the equation, you will know exactly what is happening. Okay. Okay, Manzil has also answered that. Yeah. Okay. Okay. So, Mr. Mahesh, you wanted a step-by-step demonstration on command, how to download a case file on Windows, copy it into WSL and run it with OpenFOAM 9. I'm facing issues, would appreciate detailed instructions. Okay, so Mr. Mahesh, by download exactly, do you mean from the portal itself? Okay. Because see, if you want to just download the case, it's pretty much straightforward. Okay. Okay, so I'll show you. Okay, I'll share my screen. Yeah. Okay, so my screen is visible. Let's hide this.
Yes.
Yeah. Okay, so see, if you have the portal, like say I were to download this particular research migration, you download it and it will show up in your downloads folder, right? Wait now. This, yeah. Okay, this is quite big. Let's go with smaller case. Research migrations. Yeah. Let's see this one. Yeah, this one will download fast. Yeah. So once it is downloaded, you can go to your downloads folder. Okay, so it'll be something like this, right? So you can either copy paste the whole thing or you can extract it and then copy. Now for this demonstration, I'll just copy it directly. So you copy and you go to OpenFOAM 9 or 2412 or whichever version it is on. So say I were to go to the run directory for this one. So this is my run directory for 2412 and I'll just paste it here. Okay. So once it is pasted, I can just extract it. Okay. Extract. I'll use WinRAR to extract. So once it is extracted, just refresh it. Then now this comparison of viscous this. Again, inside this, you will have another file because the files are uploaded separately and the abstract is uploaded separately. So once you're done with extracting it, okay, this one did not extract it properly. Yeah. So you get the idea, right? So you have to just extract this particular file and then you're good to go. You can just type OF9, you can just right click and open in terminal, or you can manually open your terminal and type run and go to this particular run directory. And then if there's an all run script, you can just do all run or all clean. So based on that, you can see which one is available. Okay. Okay. Okay, simulation on. Okay. Yeah, there were a few people who had emailed us also regarding this case because we had demonstrated it like in a very short manner for the awareness session that we had last time. So in that, many people had joined and they had said that we will try this case and they tried it and they were facing these issues. So we thought of taking up this case and just trying to resolve all those issues that they were facing before. Because many people said that they had kept their systems on for like a day or something, and still the results were not available. So at first we thought that it was just some commands that it was wrong or something, but then we tried to resolve that using this. We found out that the all run itself was faulty. So those commands you can just bypass them, and it runs fine then. Okay. So if there is no more questions, we can break for lunch. And after the break, we have a session on aerodynamics part. It will be taken by Pranay. Okay. Attendance link. I think it was shared before. The one. Yeah. Okay. Parisa said. So then we can break for lunch and we can join back at Pile ma'am, at what time should we join back? At 2 o'clock or by 2:10? Okay. Okay. So we can break for lunch. Let's join back.
Sorry. I was speaking, but I was on mute.
Okay.
Sorry.
Okay.
Yeah, so I was saying that now it's almost 1:06.
Yes,
So we
ma'am.
can join around 2:06 and then we can start at 2:10.
Okay, ma'am.
Yeah, people will join in and eventually we may start at 2:15, but then let's aim at 2:10 because then we'll have more time for the hands-on part.
Yes, ma'am.
Okay. Thanks. So see you after lunch.
Yeah.
Yeah, bye.
Hello.
Hello, Dr. De. Welcome.
Yeah, am I audible?
Yes, yes, you're audible. So actually, we are waiting for some more people to join. Because we in the morning there were around 160 or 172 or 180 participants. So now I can see 82, but the count will be increasing in the next 5 minutes maybe.
Okay, so you suggest we wait for some more time and then
We can, yes, yes, we can wait for maybe 4 or 5 minutes more, and around the 2:15 we can start.
okay.
Okay.
Any background sound is coming or no?
No, it is perfect.
Clear. Okay, fine.
Okay. Yes, Kamalesh. See, at this moment, we cannot do anything regarding yesterday's attendance. You please send us an email at contact -cfd@fossey.in. I'll just mention the email at towards the end of this workshop. Please be with us. Okay, then just write to us, and then we can consider it. We'll have to check our records and all. Okay, and then we'll consider it, and then we will be manually marking you present. Okay, thanks. Okay, so it's 2:15 now, and we are ready to go. We have 90 participants, and this is the last session of the 4-day-long workshop on industry readiness on open forum, on CFD open forum. We welcome Dr. Manavendra De. He is already with us. Namaskar, sir. So before we begin the session, which will be conducted by Dr. De, I'll just briefly introduce him to all of you. So Dr. De is a principal scientist at the Systems Engineering Division at CSIR NAL, and he's also an assistant professor at the Academy of Scientific and Innovative Research. Dr. De holds BE Mechanical Engineering from South Gujarat University, MTech with specialization in
பிரபு சார் இங்க பாருங்களா இங்க ஒரு மேடம் பேசுறாங்கல்ல
participants. Could you please mute yourself?
அன்னைக்கு ஃபர்ஸ்ட் நாள் அங்க அதுல போட்டுருந்தேன்ல மதியான செஷன் ஒவ்வொரு செஷன் ஆரம்பிக்கும் போது இவங்க வந்து பேசிட்டு போவாங்க
Deepak,
அலெக்ஸ்
will it
பாத்துக்கலாம்
possible to mute all the
மேடம்லாம் எங்க
participants?
இருக்காங்க அந்த
Okay, thank you so much. Yes, so I was describing the academic background of Dr. De. So as I told, Dr. De holds a BE degree from South Gujarat University in mechanical engineering, and he has done his MTech with specialization in turbo machines from SVNIT Surat. He has done PG diploma in intellectual property rights from IGNOU and WIPO, and PhD degree in applied mechanics, computational fluid dynamics from IIT Madras. He joined the CSIR NAL, Bangalore, in 2006 as junior scientist in Wind Energy Division. At present, he is serving as principal scientist in Systems Engineering Division. He holds an honorary assistant professorship in Academy of Scientific and Innovative Research, which is ACSIR, New Delhi. His research areas include applied CFD, system engineering, wind turbines, rotor aerodynamics, AS9100 certification, and IP rights. Okay, Dr. De serves as a subject expert in international and national committees. He has over 30 research papers in national and international SCI journals and conferences. He has been granted 2 Indian patents in the field of renewable energy, wind turbines, and flapping wing aerial platform. He is involved in guiding students for the final year project works, internships, and serves as a thesis examiner for PhD and MTech students. He has also guided a student from FOSSI internship, and his work will be presented as a case study demonstration just after Dr. De's talk today. So it was a brief, background of Dr. De. And over to you, sir. You can start the session. We are really humbled and we are thankful to you that you have come here from sparing your time from a very busy schedule. And yeah, we'll be happy to start the session with you.
Okay, ma'am, thank you. Is the screen visible?
Yes, yes.
And there are no distortions in the sound?
No.
Okay. So, yeah, good afternoon, everybody. It's a very challenging task. And of course, it is none of the fault of the organizers because I only chose the slot as the last speaker of this event. So just to shake you all from a nice lunch, just wanted to set the pace for this talk or the presentation, or rather a discussion, I would say. Like generally, I used to start any of my presentation with a blank slide, which would symbolize the state of an art in which the audience is expected to be. However, today we are at the last day and the last presentation, so that assumption doesn't hold true. So I would just like to tell a small story from history, and then try to say why I correlate my talk with that. So all of us know that there's a small community called the Parsis who came from Iran to India somewhere during the 8th century. So when this convoy came from there, they landed at Sanjan port, which is part of Gujarat, my home, my birth state. And when they came and they got down at the port of Sanjan, they wanted to take permission from the ruler, the king who was ruling that region during that period. And as a response to their request, the king had sent a pot full of milk. And in response to that, what the Parsi community did was they dissolved sugar in that milk in a pot without spilling any of the milk which was there in the pot, and then sent it back to the king. And then when the king tasted the milk, he accepted the request of the community to stay in that region. Now, this is as far as the history goes. So, in today's context, if I say my presentation, rather than being a milk which I would try to pour into all your minds, I would like it to be like a sugar which gets dissolved into the already existing milk, which is in the form of the presentations which the previous speakers had given in the last 3 days, and if even today morning. Uh, we had a very interesting talk, and at the same time the demonstrations that have been already given. So your mind is full of that milk in the form of all this information. So this presentation today will be more like a sugar, which will try to slightly add to the value of that milk which is already there with you. So let me first wish all of you a happy Children's Day. In India, we celebrate 14th November as a Children's Day, and there won't be any better example to learn anything rather than referring to the children's, because the children's are, they are not hesitant to ask questions. So that's how they learn. The moment we stop asking questions, we stop learning. So we need to be like a child, a small child, which will be who will be curious to understand what is happening in the surrounding, and then his curiosity leads to discoveries, and discoveries probably lead to the things that we see all around us. So on this positive note of today's Children's Day, our discussion today will be on the challenges that the renewable energy harvesting community is facing, and what can we expect from the CFD community. Of course, today, rather than carrying my portfolio as a scientist or a PhD holder, or maybe somebody who is in a government firm, I am standing, or I'm presenting my thoughts in front of this august audience, which is consisting of professors, postdocs, PhD students, undergraduates, postgraduates, and enthusiasts in CFD community. And as a common man, I'm just trying to put forth before you the issue which I am facing at the grassroots level, which is the energy. The energy is one of the problems that we are facing today in various walks of our life. And then I have something like a solution to solve that problem, which is in the form of harvesting the renewable energy. But then in that context, how this community can help me, the CFD community that can help me, that will be what will be the flow of the discussion today. So we will go in the following manner. We'll just quickly go through the overview of Council of Scientific and Industrial Research, CSIR, and then quickly go through NAL, and then have a bird's eye view of the renewable energy harvesting efforts that were put in NAL, and then a glimpse of some of the works that we did using CFD to help in our renewable energy programs at CSIR and NAL. And then finally, we come to the last portion wherein we will try to discuss some challenges and what is it that is expected from the CFD community, the FOSSI community. And so FOSSI is an umbrella under which there are a lot of open source software communities that are existing. So right now we are talking from the point of view of CFD, but as you would see, many of the problems will need help from the other disciplines also. So how does the community help us in solving or at least getting some hint on handling those challenges, and then end the talk with few thoughts of mine. So coming to the first point, basically, Council of Scientific and Industrial Research is a pan-India chain of research institutes which work on various disciplines of science. So we have labs from which work on chemical science. We have labs which work on biological science, physical science, earth science. NAL specifically, we are into the engineering sciences. So you can see all across India, we have our presence. Coming to NAL, we are at Bangalore, and our primary focus is on aerospace research. And as you can see, it is a bouquet of various disciplines that we have in NAL. You can see CFD is one of the areas. Apart from that, we have other disciplines also, composite structures, we have material science, and then electronic structures, experimentations. So all these disciplines, there are small divisions or labs in NAL, and cohesively they all work towards the primary focus of aerospace research. Now, when we do such research, it is very natural that we come out with some of the spin-offs which are applicable to the other domains also. So in that context, our expertise in turbo machines, which is very core expertise niche area required for the aerospace research, the spin-off of the turbo machines has led to technologies in the renewable energy domain. So that's where today we will have a glimpse of those works that we did, and then in that how and where the CFD community and the open forum community present over here can make significant contributions in the coming future. So basically, NL works in a consortium kind of a mode, and we always welcome networking with academia, with the public sector undertaking like HAL, the line ministries or the research labs under those line ministries like defense or Department of Space. And also we work with the regulatory bodies because it's aerospace. You cannot leave the regulations and the guidelines, the regulatory norms which need to be followed for the aircraft design. So we also work with the regulatory bodies, and also there will be glimpses of international collaboration, even in renewable energy. That was the end of the presentation, where we have done some work with uh, under the DANIDA program. So we'll have a look at it in a couple of slides from now. So as I was mentioning, we have core technologies and strengths have been developed in NAL in various verticals of research. And what we will be today talking a little bit more is about the turbo machinery, and then about the wind turbines, and of course the surveying and measurement aspects of wind turbine and solar energy. And then see how the problems that are existing can be addressed by this august audience today. So coming to the renewable energy harvesting efforts, we have again three verticals over here: geothermal energy, solar energy, and wind energy. Now, please keep in mind the things that I told in the previous slides. We are talking about the spin-offs from the turbo machines. So even here, you will see that somewhere the flare of turbo machine is existing in the efforts to harness the renewable energy. So coming to the geothermal energy, this is typically the overall architecture of the plant, where you see that our core expertise in turbo machinery has been employed in designing the turbine. Of course, when you talk about harvesting energy, I cannot just stop at only designing a component. So NAL did some pioneering work in this development of this entire system, starting with a pilot project using the industrial waste heat, and followed by geothermal energy, harvesting geothermal energy, and then subsequently solar energy also. So basically, this entire cycle is an organic Rankine cycle based power plant. So we are very well aware about the Rankine cycle, which is the thermodynamic cycle which governs the operation of a steam power plant. So in this case, instead of water as the fluid, organic compounds have been used as the working fluid. And the reason being that to change the phase of an organic uh, c- uh, compound, you need relatively less temperature gradients. And that was the thought process behind realizing an organic Rankine cycle. So this is something which we would have learned in our school days also, like what is geothermal energy and how does it get visible to us, what is the mechanism, how the magmatic intrusions they form the source of the thermal energy, and then how it percolates through the impermeable rocks and then gradually gets visible in the form of either geothermal well or hot springs over here. And there are a lot of areas in across the world where you can see the existence of such locations. And primarily, one should be aware that these areas are located in the tectonic boundaries. So you will find more of these geothermal sites in areas like, for example, in India, if we say it will be more in the Himalayan belt or somewhere here in the Western Ghats where you have mountains and there is a constant tectonic movement that is sometimes visible in these areas. So the basically this is the overall provinces in India where we can uh, see the presence of geothermal energy. Around 10.6 gigawatt is the estimated potential of geothermal energy in India. And there are various sites that have been identified by Ministry of New and Renewable Energy. You can see over here in various parts of India where the existence and the possibilities of setting up the geothermal power plants are possible. So in this context, what NL did was using the turbo machine, the entire setup was first demonstrated at NAL. This I'm talking of the time something around 1985, when many of us in the audience might not have even born. So during that period, this work was taken, and then an actual plant was installed at Manikaran in Himachal Pradesh. This was a 5 kilowatt geothermal power plant, which used the Freon 113 as an organic fluid for the Rankine cycle. Now, having done that, the next approach was to again translate the same technology for solar energy harvesting. Now, when we say about solar energy harvesting, primarily what comes to our mind is the photovoltaic cell. But there is also another approach of harvesting the thermal gradient of the solar power in various forms. So one of these form is the solar pond. So in this context, again, NAL tried to see how, again, the know-how which was developed by demonstrating the organic Rankine cycle uh, based geothermal power plant, how can we again use a different form of heat on the same cycle? So in that context, this was another program which NAL took during those days on the solar pond based energy generation. So again, here basically it is an artificial pond, and there are three layers, as you can see over here: the upper convective layer, and the non-convective layer, and the lower convective layer, which is mainly from where the thermal fluid is taken. I mean, the hot fluid is taken, and then it goes to the organic Rankine cycle, and then we generate power from there. Now, if you look at this simple figure, there are many things which a CFD engineer or a CFD enthusiast can contribute to, because we are talking about radiation, we are talking about conduction, we are talking about convection amongst these layers, and we are also talking about different phases. Phases also are available, which is at a bigger uh, level, at the plant level. So again, here, if you see the schematic, we are talking about again the turbine, which NAL had the core competence. However, extending that for the solar pond, the entire architecture was conceptualized and it was realized along with Pondicherry Government College and the local governing authorities of Pondicherry. Now, again, here, if you see, there is lot of thing that the CFD community or the open source, open form community can contribute to. So, like we are talking about turbo machines like the turbine or the pumps over here, the hot water pump or the organic compound circulation pump. We are talking about the heat exchangers over here in the form of vaporizer. We are talking about the condenser, which is nothing but the heat exchangers. We are talking about the cooling towers. We are talking about the solar pond itself. We are talking about sun and the radiation. So this itself starts posting lot of issues and lot of questions to the community, this August audience, uh, about how they can help in designing a better system. So we have some baseline systems. So given that, using the know-how in CFD, how do we improve the performance, or how do we understand the working, the operation of that? How do we forecast the power generation? All these things probably this is the forum which can answer these kind of challenging questions. So again, as we mentioned, this was again a collaborative work with Pondicherry government. The funding was from the Planning Commission through the Pondicherry government, and the electrical department, Pondicherry government, and the Pondicherry Engineering college was involved. This is the view of the solar pond, which was realized at Pondicherry, and another. I mean, there were three ponds mentioned in the previous slide. So this is the other one. And as you would have seen in the previous slide of harvesting geothermal energy, the system remains the same. So we are talking about the piping systems, we are talking about the heat exchangers, we are talking about the generators, we're talking about the turbines. There is the disassembled view of the turbine, the actual turbine which was used for generating power. So the architecture remains the same. It is the source with which we tried playing and then exploring the possibilities of harvesting the renewable energy in those forms. So in the previous attempt, it was the geothermal wells which were giving us the thermal energy, which was later on converted into electricity. Whereas in this case, an artificial way of generating the thermal reservoir in the form of a solar pond was used as a reservoir for the thermal energy. Now, having said this, let us now have a quick glimpse of the wind energy harvesting efforts. Now, the question may be there that we are talking about turbo machines, so how does this fall under that category? So, the wind turbine is basically an extended turbo machine. The fundamental definition of a wind turbine is it's a turbo machine, and it's an extended turbo machine where you, unlike a conventional turbo machine where you have casings and enclosures, here it is open to the atmosphere. So that is the reason why it is the extended form of a turbo machine. But the fundamental theories remain same. The fundamental physics of a turbo machine remains the same. So even though NAL is predominantly known for the aerospace flavors and the aerospace products and technologies, wind energy had been researched in NAL since its inception in 1959. So this gives you a chronology of various activities at NAL related to wind energy harvesting from 1959 till the present time. So we'll have some picturesque view of these things. So we started by understanding what exactly were the wind turbines that were imported, and at the same time we had some in-house designs also during 1959, 60s, and that period. So as you see, those systems were all put in the same wind farm, and they were tested to understand the nuances of the operation of these systems. You can see over here various other models. You can see here one more. And while these in-house designs were developed, there was also need to test them, the structural integrity. So this is again a glimpse of how in those days we tried to establish the structural integrity. Of course, it may look very funny today, especially when you are all aware about the sophisticated DAC, data acquisition systems, and strain gauges, and many higher level measurement schemes, experimental approaches to assess the structural integrity of any component. We have filtering arrangements, sandbag kind of things. It may look very funny that people themselves, and of course, let me mention here those who are standing over here. Some of them are the technical officers, and some of them are also junior scientists that were trying to ascertain the structural integrity of wind turbine. So while it may look very funny, if you see it from the dimension of time, this was the same time when ISRO used to transport rockets on bicycles and satellites on bullock carts. So I mean, there's nothing wrong when we first see the previous picture and laugh on that. But the fact is, like, today we have moved along. Today there is no need of telling where ISRO stands. But even ISRO during those initial days when there were a lot of technology denials to India, they had to have their own ways, and it was a very tough way, as you can see over here. So, not just the horizontal axis wind turbine, NAL also tried to understand the performance or the design aspects of uh, the lift type vertical axis wind turbine. You see a Darius wind turbine, or the drag type of vertical axis wind turbine, a Savonius rotor. You can see over here, and even various architectures of the lift type vertical axis wind turbine with straight blades. We call them gyro mills, and not just made from the metals or composites, but also from fabric. So here you can see an example of a sail type horizontal axis wind turbine prototype that was installed at NL during 1970s and 80s, during that decade, to understand the operation and the design aspects of wind turbine. And even during those days when uh, wind tunnel testing was a very privileged facility to have, NAL tried to understand the performances of wind turbines by doing the wind tunnel testing during those times. I'm talking about 70s and 80s, the decades in 70s and 80s at IISC, even our in-house wind tunnels in NAL, we tried to understand the finer details of the designs using these wind tunnel testings. Now, one aspect of harvesting wind energy is to understand the performance, correlate that with the design, and then try to do it. But the main thing is, what is the driving force? So one needs to know what is the wind potential that is available in a particular area. So in that context, NAL built the first wind map of India, as you can see over here. And this fact has been also acknowledged by National Institute of Wind Energy in their Wind Atlas map. They have recorded this fact that it was NAL which realized the first wind map, of course, with the help of IMD and other line ministries. But this was the thing that NAL did during the 70s and 80s, where when things were still germinating in India in terms of wind energy harvesting. Also, we experimented with various configuration, and one of the approaches is to anthropogenically generate the wind by mounting a prototype over a van, and all the instruments are housed inside the van, and then the van is run at a predefined vehicle speed so as to artificially generate the wind. This is an interim way of testing wind turbine between a wind tunnel and the actual field trials. The issue with the wind tunnel, as we all know, will be the various factors. The scaling issues will be there, and then you have the blockage issues because of the confinement. Whereas in the case of field testing, you may have to wait for certain winds conditions to naturally occur. So that may occur today, or that may occur after 6 months. So then it is very time consuming. So this approach of tau testing is an interim approach wherein you can artificially generate the wind by driving the vehicle at a certain speed and then acquiring the parameters like what is the electricity generated from the rotor, if there are any vibrations, what are the vibration levels. All those things can be recorded. So this is a glimpse of the tau testing and the field trials of one of the systems that was developed at NAL. And we also did the digitization of the geographic features which were proposed to be the sites for setting up the wind farms, because it's important to understand the difficulties in reaching those areas. One part is, yes, you say that there is a potential of the wind energy to be tapped in this location, but then unless we know the local difficulty to reach those areas, it may not be possible or useful. The information of wind may not be useful. So in that context, NAL also did some digitization of these kind of local geographic features, which helped in taking decisions on setting up the wind farms. Of course, it was not just that NAL did the work in India, but if you are aware, every year there are these Antarctica missions that is launched, and different countries come together and then they go to Antarctica and they do research on various aspects which influence our life. So in that context also, in during few of those expeditions, NAL went and it participated in those expeditions, and some wind resource assessment was done in the Indian Antarctica Research Station, Maitri. Of course, today we have two research stations, Maitri as well as Bharati, but during those days, I'm talking about 95 to 2002, we were having only one research station, Maitri. So a glimpse of our team, NAL team, was standing here, and the met mast which was installed there, and some wind turbines that were also installed over there for doing the energy harvesting at Antarctica, in our near to our Antarctica research station, Maitri. And apart from that, while this was going on in Antarctica, NAN also took up some activity on power curve measurements. Because having known how do you design the wind turbines, having known what is the wind potential, and having the experience of doing the entire prototype manufacturing, installing, and then doing the trial, the final thing is how much energy is it producing, how much energy the cluster is producing. So in that context, NAL also did the performance studies of various wind farms during those times when this sort of skill set was not available. Of course, today, if you ask NRCon, Suzlon, or GE, their teams do have their in-house expertise in this area of power curve measurements. But I'm talking about those days when it was still in nascency in India. So NL was the only agency, but then now today you will find a lot of people who have these capabilities. And then during the time when I joined NAL, it was working on the grid connected system. So here you see a glimpse of a 300 kilowatt wind turbine that was majorly to help one of the local textile industries in Coimbatore district. And we also had worked on the 500 kilowatt development of a 500 kilowatt grid connected wind turbine. This was also a prototype, a full scale prototype that was fully designed, then fabricated and installed, commissioned, and field trials were also carried out in the Coimbatore region. It was Kethanur. Kethanur, we had a collaborator, Sangeet, Sangeet group of companies. who had collaborated with us. So along with them and our sister labs, SCRC, we had carried out this particular prototype development and demonstration. Now, after the grid connected systems, we also ventured into hybridizing the wind turbines with the solar PV panels, because wind is notorious for its intermittency. And if we are talking about a sustainable solution, the COP30 is presently going on at Brazil, and we are expecting to have a lot of recommendations from COP30 conference on the sustainability and how to reduce the carbon footprints, reduce the ill effects of greenhouse gases. So we need a sustainable solution, sustainable renewable energy solution, which unfortunately cannot be provided by either wind or solar in isolation. So that was a thought process with which we embarked on hybridizing our wind turbines with the conventional solar panels, and we had three prototype models that we generated out of this work. So the first one was a 1 kilowatt system, which is given as a technology infrastructure to the educational institute. Here you can see some of these installation across Bangalore as well as across India, and even in our sister labs, SCRC and CBRI. And then the second prototype, that is the 7.5 and 7.5 kilowatt wind solar hybrid system, was targeted for agri pump application in a standalone manner. And the third class was the 10 kilowatt by 10 kilowatt wind solar hybrid system, which was targeted at catering to the energy needs at a community level in a rural hamlet where weak grids exist, or the grids are, the availability of the grid is not so frequent. We have often the power cuts over there. So this architecture also has the option of absorbing any other form of energy. And we had an integrated controller cum inverter, which could work in both islanding as well as anti-islanding mode of operation. Eventually, what a lab like NAL does is, once we demonstrate the prototype, we ourselves don't take up the production or the marketing or commercialization. We tie up with the MSMEs or with any companies who show interest in taking our technologies to the market. So in that context, the systems that were developed, the hybrid systems, they were transferred, the technology was transferred to a local MSME in Hyderabad, Mrs. Green Energy Private Limited, Hyderabad-based firm. These are the glimpse of that. So the technology transfer document. And as I was mentioning during the initial slides, that we do have international collaboration. So while the previous slides were more onto the product development, here it was more on the research flair of renewable energy harvesting, the wind energy especially. And the focus here was on the rain erosion coating developments. So this was a work which NL did along with two MSMEs, one in Pune and one in Chennai. And then along with the consortium also had NIWE, National Institute of Wind Energy, which is the nodal agency for wind energy in India. And IIT Delhi, Professor Puneet Mahajan, he was involved in this noble venture of looking into developing the rain erosion coatings for the wind turbines. So while we do the product development, what happens is an offshoot of that, something innovative comes out. So this particular patent came out as one of the IP outputs of our venture into the wind energy uh, uh, domain. And now, having said all these, picturesque stories, let us have a look at some of the areas in wind energy harvesting where we try to apply the capabilities of computational fluid dynamics to have more efficient system. Now, this is a nice comic from NREL, which says that, if you leave the design of a particular system, so in this case, it is the wind turbine, So if you leave these designs to the respective disciplines, how would they physically look? So, if you have an aerodynamics looking at the turbine design, you'll have very highly efficient, aerodynamically efficient blades, which are very, very thin. And then similar things happen if the control guys look into that and design, or the acoustic guys look, or the electrical engineers, if they look the architecture, or if it's a manufacturing or structure, or the weight and mass CG guys, or the service guys, if they look into the design, this is what can happen. So primarily, what we are saying is, since the final product has to optimally work, all the multiple disciplines have to come together and work in synergy. So in that context, the first thing that came out was like, this was a joint work with student Shubham Deshmukh from MNNIT Allahabad Prayagraj. He came to NL for his internship, and then he did this work on the question that we posted to him, like, if I aerodynamically shape a blade, it will have a very non-linear chord distribution. However, it may be difficult to manufacture such a complicated shape. So, in the benefit of or the ease of manufacturing, if we can linearize the chord distribution, will there be any effect on the performance? So this was the problem statement that was posted to Shubham, and with the use of CFD, he tried to answer that question. So here you can see that this is the shape of a excellent aerodynamically efficient blade, whereas this is something which the manufacturer would like to see. So when you make these two blades, how will the performance look? So he underwent all these conventional steps in CFD, like making the geometry, and then making the grade, and giving the boundary conditions, running the simulations, and then post processing the results, and then finally telling us that even if we linearize the chord, uh, it is going to produce less power as compared to what would have produced if it was a highly aerodynamically efficient blade, but the losses are not very significant. But as compared to that, if I have to make an aerodynamically efficient blade, the cost that may be involved in making that may be very high. In which case, there may be issues in its commercialization at later stage. So then we may go with a simple linear chord distribution, which may not be so efficient as the non-linear chord distribution based blade, but it will serve the purpose. So this was how he helped us to, go ahead with some practical decisions that had to be taken. Of course, another thing that he tried to do was understand the acoustics of the blade, given if you change the tip. So in fact, this work was then translated into the 5 or 7.5 kilowatt wind turbine blade design, which was for the agri pump application, off-grid agri pump application. So here again, he underwent the same rigorous process of CFD, of meshing the plates, and then doing the simulation for different pairs of wind speeds and RPM. Basically, these turbines are variable RPM systems, so we don't consider the RPM to be constant. So each wind speed has a unique RPM at which the system will become stable. So at different RPMs for a rectangular tip, and then for a SWAT kind of a tip, how were the fluid dynamics affecting the acoustics? So this is what he studied during his internship period. And I'm also happy to say that after he did his internship, he also came to IIT Bombay. I think Professor Sinha of aerospace. With him, he later on worked on single and two jet subsonic jet flows. Presently, he is abroad doing his doctoral studies. The next joint work in this direction, which I had presented during my first presentation, it was almost 1 year back, was with another student from Manipal Institute of Technology in Manipal. This was on understanding the standstill characteristics of the bio-inspired vertical axis wind turbine rotor. So again here, OpenFOAM was used for the simulations, unlike the previous case where ANSYS was used. And then these are the glimpses of the CFD, but I will leave this explanation to the next speaker later after my presentation is over, because then you will come to know much more details about the finer aspects involved. In fact, that is much more detailed and much more complicated thing that is done, and which will be demonstrated in subsequent session. The third work was with a student from Diet, Pune, and he worked on the bionic ram air turbines investigation. So basically, the ram air turbine is an auxiliary power supply unit. In fact, when the unfortunate incident in Ahmedabad happened in June month, this was one of the aspects that was captured in the video, the ram air turbine, which had popped up just before the aircraft crashed. So that was an indication that both the power plants had failed. So unfortunately, I mean, the inferences from the CCTV camera footage, which showed the ram air turbine had deployed, only indicated that, the supply, the fuel supply of the aircraft, I think it was Boeing 7878, that had totally cut off. And that's why this ram air turbine, it popped out. It was a very tragic incident in the history of Indian aviation sector. However, ram air turbine has a history of saving lives. For example, in 1983, the Air Canada Flight 143, which was cruising at altitude of 41,000 feet above ground, it faced a total energy flameout. And at that time, this ram air turbine, it got deployed and it helped the fly-by-wire flight controls of that aircraft to gradually glide and then land safely. So 69 passengers were there and all of them could safely land. A similar incident happened in 2001 when Air Transit flight number 236, that also faced a similar both engine failure condition. And in this case, around 300 plus people were on board. But fortunately, because of the ram air turbine, the pilots could safely glide the aircraft and land it. And another example of ram air turbine saving the lives of the people is what is famously known as Miracle on the Hudson River. I think that there was a movie called Sully, which was based on this particular incident, wherein in 2009, a US Airways flight 1549, which was carrying 155 passengers, it experienced a bird hit, and both the engines failed. And then the rat somehow it deployed, and with the skills of the pilots, the plane could be landed not on land but on the Hudson River. So for those of you who are interested in this kind of failure things, you can see the movie Sully, which will be very much helpful, and it will also tell you how simulations help in understanding certain reasons behind the accidents. So now coming back to our main thing, that we have already now seen what is ram air turbine and how it is important. So under this study, what we tried to do is, apart from the conventional wind turbine blade design approach, if we borrow the designs from the nature, whether what happens to the performance. So that was the focus of this study. So here you can see the unsteady aerodynamics that happens when a maple seed descends and it falls and it is rotating also at the same time. A little bit of a theory behind that, how exactly it happens. And we also are very much coming across the dragonfly's flight. So while the naked eye doesn't see the aerodynamics, when you do a CFD simulation, you see a totally different and a very exciting picture, which is seen over here. How the vortex patterns are getting generated, how they are propagating, how they are interacting with the wing. And since this is a tandem wing, we will have another way of uh, interaction. So the student, he tried to implement all these shapes in his in the open source code QBlade, and try to understand what will happen if we, instead of conventional wind turbine, if it is made a blade is made which is inspired from, say, the dragonfly's wing, or a blade which is inspired from a maple seed's wing. So how would the aerodynamics look? So this was something which is related to that. Of course, my affiliation with ACSIR helped us to also understand these things from experimental point of view. So basically, as we said, that we tried to take inspiration from the nature, and then we tried to mimic them in the engineering form by printing the shape using the latest 3D printing technologies. And then also checking whether we have got the things right or not by just holding the rotors with say two refills and just blowing some air manually, or doing a proper lab level controlled experiment here over here with proper data acquisitions, and trying to understand what the aerodynamics of this. So this was something which we did experimentally. And of course, the next presentation after my the end of my presentation, you will be seeing some more insight into how the Fossey family did the CFD part of this assessment. So that will be really interesting. I urge all of you to try to attend to that. And now we then come to the the challenges that the energy community is facing, and what is it that we are expecting. Already, while we were discussing and while we were looking at the geothermal energy based plants, or the solar pond based energy harvesting approaches, or in the wind turbine, we have been discussing this, so we can gradually increase our pace, because already we were a little late in starting. So if you see the various regions in India where the geothermal uh, uh, potentials are existing, whether it's Himalaya, North or Andaman Nicobar, Western Ghats, Godavari Basin, there are a lot of applications that are possible. Now, issues with this, primarily, one thing is the institutional challenges, which is like, there are limited R&D centers in India when it comes to geothermal. A very handful of them, you can even count them at your fingertips, so really low. So that is one thing which is holding the innovations to get into the thing. Of course, these are more related to the government, like the policy and regulations, or the financial things, technological challenges. Again, when you say technological challenge, it's more about the engineering challenges rather than getting into the finer details of the system or the subsystem level. Of course, the awareness and the environmental challenges are also existing. Now, for the policy regulation, something has already been done. It is as recent as 15 September 2025, wherein the national policy for the geothermal energy has been released, and you can have a look at the detailed document. I would just like to bring to the information of the August audience over here, which is consisting of academia, that they are recommending to have center of excellences in geothermal. And this is probably one area where a community like Fossey or the open form community can exorbitantly contribute. There's a good scope that a center of excellency is established probably in an academic institute. It could be IIT, it could be NIT, it could be a regional college, it could be a local engineering college, on deliberating various design aspects, because this is the place where you can afford to deliberate on the detailed design. Of course, the engineering part and all will be taken care by the preceders and the successors of here. But then this particular thing is something which one can, keep in mind, because here is where the integration of science and technology is going to happen. So coming to that, what are the challenges? So as we have already seen, the organic Rankine cycle at its component level is consisting of the heat exchangers, then the turbines, pumps, the piping. So there were many talks in the past 3 days which touched upon the piping and also the thermal simulations. So probably those expertise can help us to answer the question, like, given an operating condition of the plant, what is the optimal design? Okay, so it is something like a inverse design where you are given the performance and then you have to design say heat exchanger or the turbine blade and all. So here there is a lot of expectations from the CFD community where you can extraordinarily uh, contributions can be made. The second part is at the system level where we are talking about understanding the optimal design or the operational parameter. So what this means is given a system architecture, what are the conditions under which it will perform at its best or at least at the optimal level. So again, this is more to do with the multidisciplinary simulations where you're talking about fluid flow, heat transfer, mass transfer, two-phase flows, vibration, acoustics. All these aspect is not unknown to the open form community. I mean, somewhere, even if you would have done a canonical study, you would have seen these simulations happening. Now it is the time whether you can, look it from an application point of view. The same thing happens here when we're talking about the system performance. So here the question is like, given a system, if it is operating at an ideal condition, what is going to be the output? And the digital twin is more related to given a system and given an operating condition, how would it behave? So a slight difference between these two, but again here, as you would see over here, and there is a lot of thing that the open form community can really help. And today we are talking about reduced order model, we are talking about machine learning models. So that also has an extraordinary, expectation from the CFD community because the data, the clean data based on which these models also will be created is very critical. And that is the responsibility of the CFD community or the open form community if we come forward to take this challenge. Now coming to the solar energy harvesting also, since the working principle and the architecture of the overall system is similar, so you will find that many things will be matching. Like for example, if it is a pond, then these are the areas where the CFD community can help us to ascertain the optimal geometry of the plant or the correct thickness of the various zones or the heat extraction system, whether it's properly optimized, the exchanges are working properly in the material selection also in some extent, especially the lining material, which will prevent the heat loss from the bottom of the pond. But if it comes to analysis or if it is coming to the performance evaluation, you will find that what we are seeing in the previous slides also, we are expecting similar things to happen. And in fact, it would not be exaggeration if I say that each one row of these questions can be one internship problem for the interns of FOSSI Open Form 4. Now coming to wind energy, again here NIVE has released a R&D vision document. uh, I am just putting few things over here, especially to bring to the notice of the audience over here. The rotor design, which includes the aerofoil and wind turbine aerodynamics. So definitely this is the area where the open form community can think of contributing to. Of course, offshore, onshore acoustics are there, which can be also looked upon. And again, here specifically in this document, in the long-term goals, which is linking to SDG 7, SDG 9, SDG 12, and Sustainable Development Goal 13, they are specifically mentioning CFD. So it is explicitly mentioned in the vision document itself that there is a need for the CFD community to get involved in these noble efforts to harvest renewable energy. Okay. The only issue when you talk about renewable energy is the scale. So we are talking about a big scale, temporal scale, which can vary from days to weeks, or slightly lower scale, which varies from minutes to hour, or something which is varying within seconds. Now, depending upon this temporal thing, the modeling approach will also change. Like when it's second, we are talking about the CFD based model. When it is minutes to hour, we are talking about the mesoscale modeling approach. And when we're talking about the weeks or days or months, it is the global circulation model, the GCM models. So again, here, how to network these various models to realistically simulate and realistically weave these temporal differences is another challenge that the CFD community needs to accept. And I think the audience here is very much capable of appreciating this, and also they will be very happy to, I think, accept the challenge. Of course, CFD in wind turbine helps at different levels, starting with the aerofoil. Then we have CFD happening at the blade level, and then at the rotor level, and then finally at the cluster level. So some glimpses like at the blade level testing, even a very trivial looking thing like the root, if it is properly shaped, you can get something like 3.5% higher annual energy production. So this is where CFD can really, help the community to come out with an efficient wind turbine blades. Of course, we have to see what sort of manufacturing processes have to be adopted to manufacture such efficient blades. Then when it comes to rotor level, there are various approaches like the blade element momentum theory, the actuator disk, the actuator line, or the actuator surface, which have been adopted by the community. And these are also implemented in some way in the open form open form framework. The basic difference is the computational cost, which is associated with each of these approaches, and the approximation. So basically, the fan model is nothing but the actuator disk model, which is highly approximate, but the cost of computation is low. Virtual blade model is the identical thing to the blade element and momentum theory. Again, here the approximations is all higher, lesser compared to the actuator disk, but still there. And the computational times are also relatively more. We know about single reference frame and multiple reference frame models. We are very much aware of this. And the work what Shubham had done was based on the MRF models. The sliding mesh model is another approach where, for example, the vertical axis wind turbine simulation and the demonstration that you will see, this approach is only appropriate because it will not be suitable to use the MRF. Maybe the finer details will be explained by the CFD, the FOSSI family member who will be presenting the case study, and then the dynamic mesh model, which is computationally very expensive, but approximation wise, it is relatively less than all the other models. And again, at cluster level, CFD can help, understand the weight behind the rotors, or the physics which is underlying the cluster aerodynamics, and then trying to minimize these losses using the same CFD frameworks, and try to optimize the annual energy production. So it says that about 1 to 2% of the energy production can be improved if we properly cluster these wind turbines rather than just clustering them in a regular fashion. So here also, depending upon your focus, the resolution of blade, whether it is required. So, for example, if you're trying to understand the near wake dynamics, the blade geometry plays a role. Whereas if you are looking at the far wake behavior, it is not very much important to use the very detailed geometry. So here, if you approximate this as an actuator disk, you can still understand what is happening at the far wake, but not near to the turbine rotor. So this is a glimpse of the features of the wake, how it generates, and then how it propagates, and how the turbulences of different scales interact with each other. Of course, turbulence is something which even the geniuses like Heisenberg or Richard Feynman, or even Professor Lamb could not explain. So they could only give certain catch statements which are captured over here. And of course, we know about the turbulence models which can be used to capture this Reynolds stress, the two equations models, one equation model. So as we go forward to this, we probably the computational cost increase. Deliberately, DNS is not shown here, but of course, with the advent of neuromorphic computing or quantum computing, I think the audience can even dare to introduce DNS. I hope there may be some two views, but yes, I think we should try to see whether we can introduce DNS also over here. Of course, it's at this stage with the existing computational technologies, it may look a fairy tale, but may not be in say next 5 years. Of course, finally everything culminates into kind of a virtual wind turbine, wherein you have the rotor level studies happening with the wake and all those things. But of course, if you want to push the complications to a higher level, we can consider the multidisciplinary simulation problem, wherein we are talking about the offshore wind turbine, which apart from the basic wind turbine aerodynamics, will also have to handle the heaving, surging, and the swaying movements which are observed in the offshore locations, especially the floating offshore wind turbines. And then going forward, this is the wish list. Like, you can finally create a digital twin of the entire wind farm. If it is onshore, then we only need to worry about the atmospheric boundary layer. But if it is offshore, we need to couple atmospheric boundary layer along with the marine boundary layer, which will again have its own challenges. Of course, the levels of complications and the level of geometric detailings are different at these levels, but ultimately this will be something which will be really helpful to the industry. So this community, and as a longer goal or as a longer problem definition, should definitely keep the digital twin of a wind farm, and to extend the complications more, the digital twin of an offshore floating wind farm. I think that will be the ultimate challenge with this community. I'm sure with all the enthusiastic students and the professors over here will definitely agree to accept. So with that, I would just like to conclude that a lot of things are happening in the renewable energy sector, and academia and MSMEs are going to be very playing very important role in this noble venture of harvesting renewable energy. Of course, the innovative interventions from CFD community is imperative, and lot of contributions can be done from one form consortium, which we are today, having this event for. So, just like to end with a slok that from different yugas, the success is because of various aspects. So, when it comes to Kali Yuga, this is the present Yuga, it is only the Sangh Shakti that helps us to move forward. So, then Sangh Shakti is the form of consortium. So, we again, this is again, I have borrowed from my previous slide 1 year back, where the Nabla sign of open foam itself indicates that there is a need for academia and the industry and research organization like ours to come together, connect, and then try to contribute to the noble cause which will impact a common man like me, to solve my day-to-day problem. So with this, let me acknowledge everybody who has been involved in making this event a grand success. Professor Bose from University of Birmingham, the Fossey family, IIT Bombay, our CSIR family members, and last but not the least, the audience who have taken their time and they have shaken their afternoon nap and they are listening to my, please to them to help us out from this thing. And you can reach me on my emails as well as my WhatsApp credential for any queries. But rather than reaching me with a question, it is the other way round. I am actually asking for all of your help in meeting the challenges that we have seen in the past 1 hour with respect to harvesting renewable energy. So with this, I thank and I hand over the proceedings to the organizers. Thank you.
Thank you so much, Dr. Dev. It was I am not from the CFD background. Even I found your presentation very much interesting. It started with a story and ended with a sloka and so many of history, and then you are combining it with the present day, the modern technologies and all. So it was amazing. Uh, so thanks a lot. So any questions from the audience to Dr. Day now on whatever he lectured now? The questions on the chat box are welcome, and also you can unmute and talk to him.
on a humorous note, it is like, if there are no questions, there are two interpretations. That either everybody has understood everything,
Yes.
or nothing has been understood. So I take it on that positive note that everyone has understood. Of course, I try to make the presentation such that, somebody who is just starting also will be able to appreciate. I mean, there are no scary equations or no integration differentiation. It's all something which a common man comes across uh, during his day-to-day life.
Yes, yes,
So
yes. Yes, and for the students, I will mention that there is a scope of doing internship under the guidance of Dr. Day through the FOSSI internships and fellowships. So, okay, quite an interesting lecture from Twayo. Okay, Twayo, from which country are you joining? Germany. Okay.
Germany is considered to be the lead in engineering. I mean,
Uh-huh.
so it's really great to have somebody from Germany listening to our requests,
Yes,
and
yes,
they are
we
very
have
far.
quite a few persons joining from abroad also. Yeah. And the audience is, majority of the audience is students, and some are faculty members, and some are CFD professionals also. Yes, yes. Okay, but I am originally from Nigeria. Okay. Okay, so if there are no more questions, yeah, thanks. Thank you. Okay, from Shalini. Okay, so if there are no more questions, maybe we can move ahead with the hands-on demonstration part. And this work that the team will demonstrate is also a work done by Dr. Vanavendra's guidance. Manu is the student's name. Manu, yeah. Okay, so I will hand it over to Evan. You can take the session forward. Thanks a lot once again, Dr. Te.
Thank you, ma'am.
Thank you, sir. Thank you, ma'am. Thank you for the detailed session. I really enjoyed a lot. Got to know very good insights about the experimental data of how the journey has been in the energy harvesting domain. Moving further, so today's session will be presented by Mr. Pranay. Pranay is a research assistant at FOSSI IIT Bombay, and he is going to demonstrate some case study in the same domain. So, over to you, Pranay. You can start your presentation. Thank you.
Thank you, Paris. Thank you very much. Thank you for handing over. Um, Dr. Day, it was a very wonderful session, and I hope I'll be carrying on the legacy you made in the presentation by the demonstration work. Actually, there is a slight change. We right now we are presenting a different case, sir. I hope you will. Uh, it's, so right. I'll share my screen.
Okay, Pranay,
Yes.
fine.
Yeah. Yeah. Please let me know if my screen is visible.
It is visible, Pranay. You can
Yeah.
continue.
Okay. Thank you very much. Mm, okay. Yeah. So good afternoon, everyone, or good evening for many. Uh, continuing on the previous lecture, right now in this demonstration session, we are continuing to see how open foam has been used by our fellow mentors and fellow interns in resolving problems related to wind turbines. Primarily, we have good number of cases available, and one very fine among them is a 2D simulation of HDRS type of vertical axis wind turbine, which will be resolved using transition turbulence model in OpenFOAM. To open it, we'll have to open this link. Uh, Maybe after this demonstration session is over, you can personally download it on your laptops and follow the steps I'll be showing. And to replicate it on your system. I'll be sharing the case link also, wherein I have modified some case files to enhance automation and to include interactivity while resolving the case. So this case was solved by Mr. K. Sri Satya Sai Sasank back in 2022 using OpenFOAM 2112. Moving back, so let's make ourselves aware of what the problem is. So in this in this problem, the primary objective is to use a turbulence model named K omega SST LM. We'll be delving into it further, but this turbulence model is basically to capture both the laminar and turbulent transition together in a single case. And also, it studies unsteady aerodynamic loads, the wake structure, the vortices, the eddies, etc., which are a part of realistic operating conditions. Usually, 3D computational cost is very expensive, uh, and 1D simulations provide a very faint and very unrealistic idea when it comes to turbo machinery. So that's why the case which has been done by one among a fellow intern was in 2D. The right side image, it shows a general schematic of the H radius. VAWT stands for vertical axis wind turbine. We'll be seeing how VAWT is different for HAWT. Where H stands for horizontal axis ahead. Uh, in the overall case, the case study proposer has made significant efforts to build concrete mesh. We know mesh is a very important part while resolving CFD simulation, solution. So that's why the line hybrid mesh generation using snappy mesh, etc. And the flow velocity, we'll be discussing the boundary conditions too. Uh, okay, moving on to next. Okay. This is the general schematic or the top view of the geometry and the overall domain. The airfoil used is NACA 0015, a symmetrical airfoil we all might be knowing from the NACA series. The chord length is 0.4 meter, the radius is 1.25. Inlet is Inlet varies from 6 meter per second to 10 meter per second, accounting for the angular velocity of 15 radian per second. This rotation factor is important to model the counterwind flow. The model, as discussed previously, it is K omega SSTLM. Uh, it solves to equations that is basically gamma. We'll be discussing it further when we discuss the turbulence conditions and the re theta. Basically, what happens is the solver continuously change based on the input provided from gamma and the transition Reynolds number, adjust the value, and thereby it is able to resolve both the transition and the laminar cases accordingly. Uh, the next line, gamma belongs between 0 to 1, wherein 0 represents a laminar condition and 1 is a turbulent condition. I'll be showing you each of the files uh, later ahead. Uh, when when the starting condition is given, the wind turbine will be rotated very slowly. That's why it is important for laminar. And when it is shifting to a high speed or relatively higher speed, we'll be seeing different angle of attacks, which will be creating unsteady shocks. It could be shocks or it couldn't be shocks, but unsteady vortices, unsteady flow. Boundary layers will be different. It can also happen in the initial part of the airfoil while it has been rotated or it is in a startling condition. There will be a boundary layer in the laminar flow, in the laminar region. Also, there can also be transition from laminar to turbulent in some other part of the airfoil. That's why to capture it effectively, it was the idea of the presenter and it was the idea of the intern to use this SSTLM model. It is noteworthy that K omega SSTLM is RANS based turbulence model. It's similar to what K omega SST is. Just the difference which you will be seeing is two addition equations of intermittency and transition Reynolds number. Uh, since Sir has already discussed a lot on this, I'll just give you a gist on what types of wind turbines are. Primarily, we have two different axis based wind turbines. One is the horizontal axis, which we all are very familiar with. We have seen it a large number of times in the wind farms, in the countryside, etc. A vertical wind axis turbine is something the I'll if I may, the axis is symmetrical. Okay, if my I am using a pen, a green color. If you can see, this is the axis of symmetry. Okay, and the rotation is around this axis. Unlike in the horizontal axis, the axis of rotation is among this plane. Okay. One interesting fact I got to know about this type of wind turbine is this was actually way back discovered or created, or kind of mechanism was created way back in the 9th century AD. That is almost 1100, 1200 years back. Uh, It was patented by a scientist, which I'm not able to recall, but in the year 1920 to use it as wind power application. I hope the striking difference is clear between a normal conventional which we see and which is a horizontal axis, wherein in this case we are sticking with the vertical axis wind turbine. Towards the left of the presentation, we can see different types of wind turbines available in the vertical axis mode. One is the Savonius, Darius rotor, H Darius, and helix. H Darius is something which is something more common in the vertical axis wind turbine, which is used more practically, accounting for both cost, implementation, etc. And to read further on VAWT, I'll be sharing the slides, and each slide has something good links where you can read more on that on a conceptual level. Moving next. Okay, coming to the types of mesh. Since I made a line where I presented a line wherein I said mesh is the utmost important part and the pre-processing step, and without mesh resolution, proper mesh creation, all the results which we will be going through would be considered baseless, or would be considered incorrect, inaccurate, or we can come to some heterogeneous answers. So that's why it's important to have a better idea, very crisp and clear idea on when to use what kind of mesh, how to use it. We have to account for the computational cost involved and similar such factors which we are all familiar with, since we are CFD professionals. And to those who are not familiar, I'll just bring out this also five kinds of mesh highlighted here. First is the chimera or the overset mesh. Here, um, what happens is we are describing a domain, uh, and we are setting mesh based on the individual component. We are stacking one mesh over another, unlike the conventional one wherein we use a continuous mesh. I this splitting of mesh and then recombining, what happens is we can be uh, very much precise in capturing flow around the whatever body we are trying to simulate primarily, and it can be considered to be very accurate, wherein what happens with the single continuous body fitted meshes, it becomes difficult to generate because of uh, uh, large uh, sc- uh, parameters involved in the mesh metrics. It is difficult to control in the single continuous, but chimera or the overset mesh helps us prevent that. Second is the structured and unstructured mesh. Structured, we can model it very perfectly. It is good. Whereas unstructured is also very good, but it comes where how in what part and which region are interested in simulating the flow. Unstructured is basically very useful to capture in uh, in regions where the curvature is very different, wherein the geometrical curvature is different or it is difficult to model. adaptive mesh refinement, people who might be knowing shock, supersonic flows, hypersonic flows, or even flows wherein volume fraction is changing, wherein mixing is taking place, wherein combustion is taking place. We need particular, there are particular regions of interest wherein flow characteristic is very highly resolvable in that area, like shocks, like combustion, like droplet dynamics, etc. So in that region, we would prefer having a very fine, very fine resolution to account for every physics involved in that area. So that's why we prefer adaptive mesh refinement, which is AMR. Once again, it all depends on the physics, gradients, etc. And coming last to the sliding mesh. Sliding mesh is, as can be seen in the vector graphics, the mesh in fact slides. This is particularly useful in places where different regions of area is moving simultaneously. Well, we have seen a case yesterday of diesel bore engine. It can be useful there. It will be useful in our present case. Though in this case we are restricting ourselves to Chimera overset mesh, but it is a point which can be noted. Sliding mesh is very useful in the turbo machinery area. Once again, to read further on mesh of quite basics, you can refer to the wiki links shared. Okay, moving to next. Uh, Now let's discuss on turbulence. I'll be coming to the hands-on session very soon. It is very important for me to uh, tell you about all this before we solve. Mm, just okay. So here we are in this turbulence model SSTLM. We are solving mainly six equations. Three is of momentum, XYZ momentum. Then one is pressure, which is also known as the Poisson equation. Turbulence equation of k omega, which is turbulent kinetic energy specific dissipation rate, and the last two, intermittency and the rate eta. In open form, we can call the RAS function in the turbulence property, and then we can use the keyword k omega SSTLF. Uh, so that open form knows we are using this particular kind of model. Next. Uh, this is the particular equation wherein towards you can see in this it's a form of Navier-Stokes equation, which it's it looks like the Navier-Stokes. Okay, so here gamma, here re theta, it's all accounted for. Now this is something professionals very who are very eager to know more, they can delve deep dive into it using the links shared here. One is the very good documentation provided by NASA on how this Langry-Mentor model has been solved, and the other is how OpenFOAM is implementing it. And now coming to the simulation part. Okay, so in our simulation we have different dictionaries. Since we are almost on the culmination of the OpenFOAM workshop, we are very well aware of all this. I'll just revise all this. It's primarily our objective is to have a very high quality body fitted aerofoil, which is obviously NACA 0015 with a course background, because we are more interested in areas towards the aerofoil, towards the wind turbine, than in the background. Okay. So first, primarily block mesh. Block mesh is used for overall. It is a dictionary which creates structured blocks, and it will be used mainly for the background. Snappy hex will be used to create complex geometry based meshing. And extrude mesh, it will be extruding a cell in the Z direction. As we all know, OpenFOAM is FVM based, so to add volume in a 2D dimension, in two-dimensional case, we need to extrude it in the Z direction by a unit distance of single cell. Create patch once all, since we will be creating mesh independently of each other, there will be no single step mesh creation. So what happens is when multiple times we'll be implementing mesh commands, we need to be after we need to be very careful in what patches are we assigning, because this patches will be something which wherein we'll be defining the boundary conditions. So that's why the create patch tool, merge meshes and topo set. Once again, for we'll be seeing how four different meshes are being created and then merged together, and then topo dictionary is used to assign variable the values. And the set fields, there are basically two straightforward there are two ways in wherein we describe the values given to the input file. It can be explicitly mentioned as in a patch, or we can mention the values in every cell using the set fields dictionary. So let's start with the case. This is for the people who will be going ahead sometime later in the day. They need to be aware कि in each of the case, in our case, I'll first show you my present in the case dictionary. I'll be opening my terminal. Here we go. Okay, so I have already downloaded this case. Okay. And in this downloaded case, you will be finding mainly two folders. One is case directory and second is the report. This all run and permission all run is something what I have created for you people to explore later. Excuse me. And I first primarily will be entering this case directory, and I'll show you what are the different things in here. Here there are folders: aerofoil C, pimple, and simple. So aerofoil C is something we'll be working on now. Pimple uses over pimple form, over pimple dy form, and simple uses over simple form. This over before the command is just to show that we are using a mesh of category overset, so that proper interpolation by the solver can be done when different meshes are stacked over each other, and proper calculations needs to be accounted. That's why a specific set of solver has been used. Let's enter the case directory aerofoil. I went using cd. I presume the audience is well aware of basic Linux commands cd, ls, because since it's towards the last stages of the workshop, it's the penultimate session, in fact. Uh, I'm skipping on that thing. So to list more on the file contents in this, we have uh, we have aerofoil overset, snappy hex mesh. We have the background snappy hex mesh and the background overset. I'll
Renan,
yes. Hello.
to interrupt you, can you
Yes.
just zoom it a little bit?
Yeah, sure. The terminal you said, right?
Uh, no, you can just increase the font size. Yes, yes.
Okay, fine. Okay, I'll. So once again, let me show you all the different dictionaries in the visual format, in the graphical format, in the icon format, whatever you would prefer to know. Uh, Aerofoil overset, snappy hex mesh, background overset, and snappy hex mesh. Uh, the um, the intern has set a certain guidelines to follow, and that is mesh needs to be created in a step-by-step manner, which is first we would need to have a background mesh using for the airfoil, and then we can use the overset. Then once again we'll have to create the background mesh using snappy, and then we have to combine the background overset mesh. Okay, I'll be showing you each step by step. uh, so for the people who are very new, I suggest you please follow step by step, and do not refer to all run all and all run dot pre etc. Just manually enter the commands in the terminal when you will be doing it. um, and I'll show what is the difference between uh, each of the steps, why the four steps are needed. Uh, mo- Moving on. Okay. So, okay. And yes, please make it a habit when you download the case. Please go through the README files. Yesterday also it was set. The Fauzi team has some guidelines while uploading the cases, and that's why one among them is having a very clear, crisp README. So please go through it. If you get stuck, revert to us. We'll be definitely helping you. Okay. So first step here, the user is suggesting, or the thing is, let's generate the snappy X mesh. Okay, and then uh, okay, terminal. So we'll be going to the readme.txt once again. Nano, and then we'll be implementing the allrun.pre, opening the allrun.pre. The allrun.pre has all the commands which you need to put step by step for the successful generation. Okay, the first step, we have to enter the snappy hex mesh and run the all pre commands. I hope that the participants are following on what I am trying to emphasize. Uh, or else we also have, I also have something. mm, I can, okay, interactive ways. Uh, so once, so there is this all run which I highlighted in the starting part. So this all-in what is does is it creates something interaction based workflow. Uh, Highlighting time, I'll be referring to the switching to this as and when needed. So we have three cases which you saw. State. Please ignore this. This is a typing mistake which came in. It was inadvertent error. So we'll be running the case error file, and then this all is created using a bash script and the all run script using bash. So every step, everything is highlighted in what are we going to do after every command, what is the expected result, why is it necessary, or how you can implement yourself in your terminal. So this is it. I'll press enter. The first thing is all clean. Do you want to clean? I'll just skip. I skipped it. So that all run was basically to show you how you can be mimicking the exact thing without getting any assistance from us. Okay, and it has been taken care. Okay, every step is modeled perfectly. There might be bugs, there might be some issues, but it's mainly the case will be resolved. I hope I conveyed what I wanted to. Moving, let's switch back to the original version. Uh, and the manual CD careful. Now I'll be copying pasting the commands all each step by step. First, it's yeah. Before pasting the commands, it is important I show you what is present in each of that. Okay, so in the aerofoil snappy hex. Okay, first block mesh is getting created, and then we have once the background is getting created, we are fine tuning it and fine refining it. That's why the snappy hex and dash override represents whatever created previously should be neglected and rewritten. Okay. So I'll just copy this to commands instead of run cd. Airfoil snappy. Okay, first command was block mesh. Done. And second was snappy. I need to show you how it is. So I'll be opening it using Parafoam. Please have a look at this, people. Normal two-dimensional with a unit dimension in the Z is been created. So this was the first step. Now the snappy hex. So this is how snappy hex iteration looks like. The way different parameters and different variables come into picture. We have to be very specific in defining all this. It is something, it is an advanced meshing utility of OpenFOAM provided. And it takes some certain, not certain, but really more than the word certain amount of practice to get familiarity with this kind of tool. So this mesh generation will take around 90 seconds on my system and will vary from system to system. Once it is created, we'll wait for some time and I'll show you, once it is completed, I'll show you how the mesh looks like. Uh, Also, unlike commercial softwares, here there is no direct visual representation unless the mesh is properly made. So let's see how the mesh was generated. So previously it was just all rectangular square blocks. Now we can see specific regions of interest has been created. Okay. Uh, no, and there is no, and this darker regions is the area, is a specific area where we will be placing our aerofoils ahead. I'll just see. It is very important to note how fine the area is compared to the overall mesh. Okay. Now you might be perceiving it as a as a solid object, but later ahead we will be able to see how that portion is getting eliminated. So now moving on to the next thing. Once done with Snappy, we'll have to use the aerofoil overset uh, folder to generate further. For the aerofoil overset folder, once again, the same thing exists. Sorry, here exists extrude mesh and create patch. I'll be quitting this, moving to the terminal. Until this was the first step of mesh generation. I'll be switching back to the previous directory and moving to aerofoil overset. First, I need to use the extrude mesh command. This implementation is very quick since we are only extruding by 1 unit in the Z direction. Particularly this, now you might be able to see how the solid region which was seen previously is eliminated and perfect aerofoils is coming into picture. You might see it is see-through. Yeah. One thing to note is in the dictionary of extrude mesh, we are sourcing it. Everything has been sourced in order. So right now the source case, it is referring, please refer to this mesh already created in this directory and apply the necessary changes mentioned ahead. Okay. And similarly for create patch, now comes create patch. Here we are going to define the patches, inlet, outlet, and the walls. Create patch, override. Override is a function utility which offsets all the previous data and creates a new one in place of it. So to read out all this, we can see a new face of wall was added. Uh, Empty face was added, which is the front and back patch, and the oversight patch is added. Now, since the airfoil generation is done, we'll be moving on to the background mesh generation. CD background. So the next command, next sequence in the background generation is block mesh and snappy hex mesh. Similarly to it, I'll show what the difference is in this time. Yeah, we are into this directory background snappy hex mesh. So first block mesh was created successfully. Once again, very simple. And now snappy override. Created. So particular small area was finely refined. Uh, So this was the change which took place in almost 1 second or 0.62 seconds. So the 4 steps of meshing are done. I hope everyone has followed the difference. We'll be seeing how it combine, how the next process of combination takes place. So for this, we'll be shifting, we'll be entering the this directory. So we'll have to switch back. Right now, we are in the main directory of aerofoil. We'll have to enter background overset dictionary. So this okay. And here there are two things: all run and all pre. So first, all run pre needs to be run. Inside now, 4 steps of mesh generation is done. Now we'll be combining it and running the solver. I hope the steps have been cleared until now. So once again, we'll be following this set of commands. This all things, it cannot be something which can be mugged up or by heart or by something. This is something you'll have to follow rigorously. You'll have to follow the readme files. You'll have to have the intuition on what command comes first, what command comes next, on what is that command creating basically. So this all can be only understood once you're doing it hands on. As of now, I'm just following the set of commands, copying, pasting it. It might seem like that, but it all comes with the experience of the user. And when you delve into it, you will be realizing on switching and coming back and forth all every time. So this to overcome this, I also have the all run in the main directory, which will be bypassing it everything. And you just have to given the terminal the input of yes, no, skip, or the numerical value, and all things will be done accordingly. So that was slight off topic deviation. So let's create all this. Okay, one thing you will be noting here is run application. What happens is run application is just a keyword. Here, if you follow this, there will be no terminal based output. Okay, it is something commonly used in the all-run scripts. But run application, what happens? See, extrude. I write extrude mesh. This number of finite steps have been generated. But when I just use a run application and combined with extrude mesh or any other function, I'll just get command run successfully and the last line. Okay, so that was the point of something I wanted to highlight. Extrude mesh is done. Next comes create patch, overwriting the existing patch. So this is something we'll have to merge. Let's see. I'll show you the mesh generation until now. This is not the complete mesh generation. Okay, with this input, I just want to highlight where at what point we have reached uh, in 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 the merging of the meshes. I'll show it again. The resolution wasn't clear then, so please note this is not the correct thing. Since it is incomplete, it is just showing some heterogeneous values and heterogeneous representation. We'll be hopefully seeing it perfectly later ahead. Okay, coming to the last set of commands, topo set. Topo set is can be found in the topo set dictionary. Here we are assigning certain values based or we are assigning field values in a particular region of interest based on the coordinates of that area. Um, yeah, that's it. Topo set. The cell set keyword here is something you should note. It is a particular commonality number of cells or a certain number of cells which have common feature can be assigned using cell sets. And then comes tolerant pre. That was the final step. And now we'll be using restore zero dictionary. That is optional. Or if you already have uh, if you already have a zero file, it's okay. Or else you can just copy paste it and rename it to zero. So 0.org means 0.original and zero is zero. So all the contents can be saved and preserved in 0.org and you can constantly tweak in this. So let me go through all the subfiles, the files which we all as a beginner might be finding interesting. So the P file, which is of pressure. Here we are calling the value of pressure from a certain dictionary, from a certain input file. The boundary conditions are all you might be familiar with, the zero gradients and all. That is not something we'll be discussing right now. Uh, theta values. So the user has decided to give an input value of 160.99 for initialization purposes. It needs to be initialized, right? Every CFD solving needs to be initialized with some certain values. So based on the discussion, based on the calculation, or based on the interest, this value might have been derived. Please note that. And something epsilon gamma is again initially gamma value is 1. That is in fully turbulence region. Data will be constantly changing based on solver. I'll be showing you the field values ahead. Uh, and yeah, in the include is a folder uh, which contains few information like flow velocity. Flow velocity is in normal to x direction with the value of 10 meter per second. Turbulent kinetic energy, turbulent omega, and turbulent epsilon value is also given. So that's why we are not explicitly mentioning it over here. Or else, if we would have mentioned it, we would just need to eliminate this keyword. I hope that was understood. And now I will be running the solver. So, uh, since this is very complex case, running this would take more than few days. I would like to tell you, I solved this case starting from zero with a delta t of 1 raised to minus, sorry, 10 raised to minus 6. That is almost, there was interval of 1 microsecond after every solving. And with that small time, with that very small time set, our objective is to contain the CFL values or the Corin Friedrich number to 1. CF, since this is a transient simulation, we need to have a CFL value less than 1 for the solver to progress and capture correctly the flows. I'll show you how it is. The solver in our context can be found on this is the solver. Over pimple dy my phone. DYMF phone. Over refers to the overset part, and everything related to the solver can be found.
లేదంటే
Hello.
అయిపోతావు. నాని అంత మంచి కాదు నేను అంటున్నాను.
Rene, you can continue.
Yeah. Everything related to the solver can be found on the documentation page for further study. So I'll be running it on a single code just to show how the simulation progresses. I have run the case until 0.0009 seconds, which took almost more than 48 hours. Please note that in a very good system. So I'll just enter this. So at every time step, at every right now the delta t is 3 raised to 3 into 10 raised to minus 5. It will keep fluctuating. Please note that because our time step is not fixed, though we are explicitly mentioning to keep a time step of 0.001, but over we are oversetting it. Oh, sorry, we are bypassing it with this keywords adjust time step and max score. Had it been 10, it would have a significantly larger time step. Had it been 0.1, you could expect a reduction in order by 2. A reduction in that is right now 10 raised to minus 5. You could see 10 raised to minus 7 also to account for this CFL, or max score stands for max current number. So yeah, the solver will just now keep on iterating until very large time, until the end time is. This is usually how this terminal looks like when the case has been resolved. So since we cannot wait for 48 hours to see the contours, we can see some using the already one, or using the already. I'll bring a stop to it. I'll show you the contours I have. Okay. CD. Okay. Uh, Allow me a minute. I'll just bring out the file. Until then, I'll be stopping the share.
Sure.
Yeah, my screen might be visible right now.
Yes, Pranay.
Yeah, thank you. So, okay. So this case is resolved up to 0.00975 seconds. I'll show you how the contours look like at different time. Yeah. So first we'll be applying it, and yeah. So one among the things which you should, which as an observer or an audience should have clicked, there is something which is sliding out here, which is a pointed thing which comes out of the domain and enters there. Uh, this is this is a feature. This can appear like a sliding mesh, or it can be right to call it as a sliding mesh for some. But please note there is just a rotation induced in the mesh region. Sorry, a rotation induced in the areas of interest. That is the area wherein the wind turbine or the aerofoil is getting rotated. No, the entire domain is not getting rotated. Just the specific region of interest is where you will see the rotation. Had we trim it further, we would have not seen this thing elongating out, emerging out of the domain. And please note, there will be no calculation error out here because the user has accordingly set the values. That's why it is something which can be noted as an observation. Nothing serious, nothing much on that aspect. So yeah, this is something the pressure contours. If I permit, okay, I'll be changing the U part. We are also able to see the vortices created. Okay, and if I set it to, and then gamma into values, not now. Yeah, so this is the turbulence number also, the transition turbulence number. Basically, all the fields which have been solved or which can be resolved by changing this is what I wanted to imply correctly. And now moving towards, it's almost done. So as an user, if you want to follow every step, you can just copy paste this commands step by step, and you will be able to replicate the exact same thing which is on my system. Uh, the user has also validated the performance with a benchmark NACA 00 airfoil also, a single airfoil. So validated the solver he used. Uh, Please note this is a single airfoil simulation which he demonstrated and not multiple. Yeah, this is the contour of velocity. Uh, yes, there will be a difference. You might be seeing the contours here and the contours shown in my system, primarily because the solving has been done for a very long time and then the contours are obtained. And however, that is not possible unless I have a very good workstation wherein I can keep it off for a very large number of days and forget on and keep doing my normal work. I hope that would be something appreciated. And last, the velocity contours was done. Now the pressure contours. So here you might be seeing the stagnation point is getting well resolved, the point zero, wherein the velocity is getting zero. And yeah, so towards I'll be concluding my case now. So if you want to explore more on the cases available on wind turbine, we can refer to case number 32, wherein once again VWT is modeled. 133, which is the present case, and 176. This case was done under Dr. Day's guidance. This is a very good case, and it will be very interesting. And this case is something which is done very recently. Um, it combines both the biological aspect that is inspired from the nature and the conventional aspects. So we all particularly insist on explore those cases. It will not take much of your time. We do not expect we would be very obliged and very happy if you could in, delve into it more. That will be the flotation of the workshop. But what happens is all you can do is download the case, just execute the all run files and see the results. You'll see is you will appreciate the things which OpenFOAM and is being able to do and handle. So yes, um, now okay, now yeah, that was my last slide, and thank you once again. I'll be sharing this automated files. I'll show you how the automation looks like in one single step, and then once I share it, you can download and just execute all the permissions. Mm, CD. So here, primarily, there are two scripts. One is the all run, and one is the permission all run. What happens is once I transfer these files to you, all the executive permissions given to the all run, that is chmod plus x, wherein the system will be able to execute those bash scripts, will go away if those permissions are not given. So that's why to execute to give it the right and execute permissions, we this permission all run is there. So to execute the script dot slash permission all run, this will pop up. And once you write yes, you'll be seeing wherein the all runs are present and the permissions have been granted successfully. So almost 23 files have been granted these permissions recursively. The script recursively searches for all the files starting with A or LL or UN or all clean. And then you have to run the all run script. All run. Select the case. It starts with HDD vertical simulation. It starts with you can select any of this. Once again, uh, please ignore the description in the first two. So I'll be selecting the first case. Uh, a general overview has been given, and then the workflow steps. As you might remember, we followed first entering the Snappy Hex dictionary. Sorry, we the Snappy Hex folder containing aerofoil. The first step, then the overset, then once again background Snappy, then the overset. The sequence I remembered was SO. So that is what is happening here. S once again aerofoil O, background S, setting up O. Okay, that is just a layman trick. You can have yours as well. So do I want to run the all clean? All clean will eliminate or delete all the files which have been there. So I'll be moving next. Uh, so uh, First step, generate aerofoil mesh using why? Because we are creating NACA 0015 plate with approximately 45,000 cells in the boundary layer. Accounting, we are also taking care of the Y plus values. That's why this much number of cells. So it will also be shown run block mesh plus snappy hex. So just write yes. It will keep working for the next 90 seconds or unless or until the amount of time you see. I'll let this run and then I'll show. I've also added this feature wherein after every step is getting executed, you will be able to visualize it in the script itself. Otherwise, you would have to go to the different directory, open it, navigate and open it, then enter parafoo to visualize it. But the script would bypass that. This is for people who like to skip the hard work and get things automated. This days I'm just bypassing everything. Okay, until this case is running, I'll share the download link. Uh, so this drive modified case with automation. Uh, so I've shared the drive link in the chat box, and I'll also be sharing the original case. Please note I haven't changed any of the physics involved. It's just the execution steps. Uh, yeah. Uh, it was generated 1 second in 80.83 seconds. If you want to see the generated mesh, just write enter. Sorry, just type yes. Also, this command, you might be, it will vary from user to user. Right now, I'm in this directory. You might be in some other directory, and this should change. Okay, so this is until this region, this is the directory, and this is the command paraform built in. Simple paraform also works. Yes, paraform will pop up. If you guys might have remembered, this was the very first mesh which we saw. Okay, then press enter to move to next. It says, do you want to go to the next step? I would say yes, I very much want to go to the next step. It is something very quick. Once again, this will be, so what I showed you in the last 15, 20, almost half an hour, I could have used the shortcut and wrapped up in 5, 10 minutes. So that is the beauty of the script. Yeah. So I'll not run further because you know what happens ahead. There are two more steps and then running the solver either on single core or on parallel. Okay, I'll just press Control C, and with this, I'll I'll rest my case. It was nice. It was nice presenting to you. Thank you. Over to you, Palma and Paris.
Yes. So any more questions for Pranay?
Pranay, there is a question in the chat box
Yeah.
regarding how to change the rotation speed. So if you have any idea about it, you can.
Yeah. Okay. I'll just highlight the dictionary if it is there. Uh, uh, okay. And this should be Mm, yeah. So if I'm not wrong, you will have to call the dynamic mesh dictionary in the constant folder, and omega. Omega is the rotation value which we will be given. I hope my screen is visible, right, Paris?
Yes,
Yes,
it is.
Yeah, yeah. So in the background overset dictionary, in the background oversets folder, in the constant subfolder, we have a dynamic mesh dictionary, and into this we are calling the dynamic mesh overset library, FV mesh library, and in this we have the rotation speed axis. I am not very much sure on the units, but in general, the origin is defined, the axis x, y, z direction, and omega, it should be radian per second, or it could be, yeah, that is the speed part. I'm not very much sure, but yes, this is, you just have to change this value to get the desired rotational speed. I hope that would be clearing the uh, that would clear the doubt. If, yeah. Any more questions? Yeah, how to run last time step so that it take 48 hour or more. Last time step so that it take 48 hour more. I didn't get this question actually. So basically, you just have to keep your system on, keep it untouched. What happens is, if you fiddle with the system, what happens? You are basically consuming the resources already. So RAM allocation will be different. Thus, load on the CPU will be different, and that's why the 48-hour thing was given. Even if I keep it on the workstation with 8 cores or even 10 cores, it will easily take uh, this much amount of time. Okay, and yeah, if you want to use the last time step, you just have to, in the control dictionary, uh, use the keyword latest time instead of start time. Sorry, instead of start time. Yeah. Uh, uh, I so if I write start from should be start time, it will start from 0. But if I write start from latest time, uh, it will start reading a last file saved, last time step saved, and and with that you will be able to. Mr. Mohit, I'm not much aware on this, so you'll have. I'll come back to you. Maybe. So, okay, Manjal has answered.
Okay, any more questions for Pranay? Otherwise, we will move on to the next sessions. In the meantime, just I want to share the feedback form So the feedback form is very important because the name and the institute name that you are going to fill here today, that will be printed in the certificates. Okay, so this feedback form will be given to you through email also. But for the time being, you can just copy it. And if possible, you can just fill it. Whoever is free now, you can just fill it.
Just wanted to ask, I hope I did justice to previous session of Dr. Days on simulation of wind turbines. Any input from Doctor?
Any input from whom, Pranay?
Dr. Day?
Dr. Day is
Yeah,
not here at
I'm here only.
Okay,
Yeah.
okay.
Yeah, I was following the whole presentation. No, it's excellently done. Like overset mesh, I've been only hearing, so it was a good opportunity for me also to see the application. So yeah. Only thing is like now the setup is available. So now a more realistic thing, like taking more realistic values, maybe a realistic aerofoil shape, and all those things can be then considered gradually. Maybe that can go in as a research mode. The baseline is already done. That too, this automation was really good. In fact, one of my student who is working on the morphing aerofoil just now, he is also completing his internship. He's from BITS Pilani. He has also done similar thing, like he has automated the whole thing, so he doesn't have to like physically be there. He just runs that script, and then the whole simulation keeps on moving, and then also assembling the whole thing. So there are a lot of nuances to that. So yes, it will be a very good thing to have all these things in place, so that once these elements are available, then you can actually get into the applied CFD, wherein we take the real world things and then start putting them, implementing them, and then that becomes helpful for the entire research community as well as the industry and the associated stakeholders. Yeah.
Thank you for the feedback, sir.
Okay, so with that, I think we can move on to the next part of the workshop. So the feedback form, as I mentioned, will be emailed to you after this workshop. So now let me make a small presentation that will help you to learn more about the internships and fellowships that FOSSI offers. Please, I'll share my screen and present. I hope my screen is visible.
Yes, ma'am.
Okay, so here we are. We are done with the technical part of the workshop, with all the talk sessions by the advisory board of CFD team of FOSSI. And now, what next? What next after this workshop? So this is just the beginning of your learning that I would like to mention, that it is not the end of something. It is just a beginning of a new thing. Okay, so you can associate with us, you can stay connected with us, and you can do very well in your CFD background. Okay, so this is the next steps. Just after the workshop. Step number 1 is go through all the spoken tutorials on OpenFOAM available at the resources tab at the cfd.fossi.in. So just after this talk, I'll take you to the website and walk you through. Step number 2 is please explore all the completed case studies and completed research migrations. So let me explain what are the case study project, and what are the research migration project. So cases are basically small problems on CFD that can be solved using OpenFOAM. Once you are, once you learn OpenFOAM and once you know how to use OpenFOAM to solve CFD problems. So those are cases. So case study project is a basic or elementary thing that any student can take up and they can submit. And research migration project is one step ahead or one step higher as compared to the case study project, because here it is actually applicable for the people who are doing PhD or research. Like they can refer to any problem that is already been published on a renowned journal or any conference proceeding, and then that problem can be replicated. That CFD problem can be replicated using OpenFOAM, and that's what we call a research migration. And there is something called lab migration also, wherein FOSSEE actually helps the education institutions who are using commercial software, paying hefty licensing fees to migrate to OpenFOAM, which is a FOSS, and that can be used legally, using the free licenses that FOSS has. And step number 3 you'll have to propose a case study or research migration project by yourself. So if you are a student of an internship or fellowship project of FOSSEE, then we'll guide you throughout the process how to do it. But as a student or as a faculty member, anybody is welcome to propose and complete and submit a research migration project or a case study project. These two projects and even the lab migration project, they are open for all throughout the year. Anybody can participate. And yes, the participation has certain rewards. I'll come to it. Okay, so how to propose a case study or research migration project? There are certain steps. First of all, you will have to come up with a topic. Okay, any topic of and that you are familiar with, that is of your interest in CFD. Okay, and then you have to correct to a guide. That guide can belong to your own educational institute or any professor from the CFD field whom you think that he or she can guide you. And in case you have a topic in mind and you cannot locate a guide, please write to us and we will try to arrange a guide for you, a faculty guide for you. Okay. And actually many people do in this way. Like recently in this year, we have got some submissions on case study. And those students were not a part of our internship or fellowship programs. They just did it out of their own interest. Okay, and it's a great value addition in their career, because these submitted projects will be published on our website, and this website is viewed by the the MOE and the government bodies. We send the report annually and quarterly to the ministry, and actually your names, that the people who are publishing the research migration project or case study projects, their names are with the ministry. Okay, so it's a very prestigious thing also to participate in the FOSSEE project. Okay, and then you'll have we have guidelines for all the case study and research migration project. I'll just navigate you through our website, and then you will come to know. And finally, you have to submit. So we have very clear instructions on how to go about it. The guidelines, we have guidelines for everything that will help you in each and every step. Okay, and yes, recognitions are, just I mentioned, your work will be published on cfd.fossee.in. We will be awarding you certificates and honorarium also. And the best part that that comes as a reward is the experience or the knowledge that you will have, and that you can take it forward to your higher studies or to your jobs that you are applying in future. Okay, so these are the rewards. Now let me come to the internship and fellowships part. So we are about to end this year, and this year for the core OpenFOAM part, we are not offering any more internship or fellowship programs. The recent one that is going on is the autumn internship. Okay, so we had semester-long summer fellowship and autumn internship this year. Then next year, from 2026 January onwards, we will again announce the semester-long internship. Okay, so these semester-long internships are offered as a fully online course. 3 months is the duration. Okay, and summer fellowship is, we offer it in a hybrid mode. Like fellows who are interested to stay in IIT Bombay campus and do the fellowship, they are welcome. Otherwise, many people opt for online thing also. But there is no guarantee that if you come here at IIT Bombay, faculty from IIT Bombay will guide you. Because we have a system wherein we have many faculty members working with us as faculty partners, and they are from all over India, even abroad. Okay, and we have a double blindfold blindfold method of mapping topics that the faculty partners flow, and the topics that are of the interest of the fellows who are applying. Okay, and we have some system of ranking and allocating topics. So anybody can be assigned under any faculty member. So it is like that. So sometimes it happens like Professor Manaswita Bose is a faculty member from IIT Bombay, who is the co-PI of the FOSSI project. And she actually guides students under internship and fellowship projects of CFD FOSSI. And there were one student from IIT ISM Dhanbad this year who happened to be under Professor Manaswita's guidance, and she opted to come here and work. And so that girl actually got the opportunity to sit at Professor Manaswita's lab and do the fellowship. Or else it is equally effective if people are doing it online. Okay, just I remember, I think most of you were attending Harish's talk yesterday. As he mentioned, Harish's fellowship was also online. He did under Professor Dheeraj Garg of SNU, Noida. So this way it is convenient. I mean, online is also okay and in person is also. So this is about the summer fellowship of FOSSI. Autumn internship is also fully online. Okay. And selection criteria is very interesting. We only select the fellows and interns based on a screening task that the CFD team of FOSSI floats. And we do not check your marks that you secure in your exams, in your college exams. Okay, and we do not see any of your rankings in your college, any of your past report cards, nothing. We are not interested in anything. We are just interested in whether you are trainable or not, whether you have the interest to get trained on a subject, for example, CFD. So it is like that. Okay, now the announcements and details are available at FOSSI.in, because whenever we are announcing any internship or fellowship, we always announce it through FOSSI.in. So please keep checking FOSSI.in probably every month. Like we may announce it in January or February. Okay, and just after the semester-long internship, we announce the summer fellowship. So summer fellowship is announced around March. So please keep checking FOSSI.in. Also, I announce everything on LinkedIn. I think all of you are connected with me through LinkedIn. Okay, I have my profile there. Okay, so you just follow my posts, and whenever any internship and fellowship is announced, I actually do it on LinkedIn. So, and also FOSSI has a LinkedIn page. You please get connected through us through LinkedIn also, because from FOSSI page also we announce this internship and fellowship. Okay, so this I'll come later. Let me just show you the FOSSI website. So this is the CFD FOSSI website. cfd.fossi.in is the website. Very simple. Fossi.in is our parent website, and cfd.fossi.in is our CFD website. Here you have got many tabs. See. So just click on the resources tab here, and you will get all the resources to learn OpenFOAM. So these spoken tutorials are audio video tutorials which you can use to learn OpenFOAM in your own learning pace. Okay, whenever you have some free time after your college hours, you can just go through all the spoken tutorials. This actually starts from the very basic level. People who have not installed OpenFOAM, it will help you to install OpenFOAM, download the necessary files. Okay, then it will start from very basic cases. Okay, and it will take you to the intermediate level also. Okay, so please, your first and foremost job after this workshop is to go through each and every spoken tutorial on OpenFOAM that is available here. Okay, then I was just talking about the case study project. So see, if you just click on the case study project tab, you have the procedure, you have the guidelines, okay, how to propose everything, every step is mentioned over here. And if I click on this one, completed case studies, you can see all these case studies, and these are submitted by people like you, students like you. Okay, they are not, these case studies are not done by our team members. They are people like you. And you can see, the institute's name. Many are from IIT Bombay, but many are from different other universities of India, and some from abroad also. Okay, so these are the completed case studies. So, see all the solver names are here, the topics are there. If you just click on it, you can download all the case studies, the actual cases and the reports. And whatever case studies you feel are important for you in your career, please learn it, please replicate it. Just like the way my team members showed you during the workshop. Okay, so similarly, we have the same thing for the research migration project. And for the lab migration project, actually, we need two parties actually to contribute. The lab migration project is actually proposed by the faculty members. So there are many faculty members who have joined in this workshop today. So if you're interested to collaborate with us for this project, for this lab migration project, please write to us, and then we can I'll just explain you the process. So the process is, you'll just have to make a list of experiments that are taken up in your institute under the lab, under any of the lab courses. And then we will have to find a solution provider for all the problem statements. So that solution provider you also can find from your own institute, some other faculty member who has the knowledge of open form. He or she can contribute, or any PhD student or anybody whom you know who can be the solution provider can be involved in this project. And we have a certification and honorarium for each and every project. Okay, all these lab migration projects, research migration project, case study, we have honorarium for everybody. Okay, so what else should I mention? I think that was enough. And yes, for the faculty members, one more thing is, if you want to guide your own students on the case study project, please write to us. Okay, we will let you know the steps. So with this, I'll stop sharing. I'll come back to my presentation later on, and I'll request Dr. Chandan to interact with the participants and take it forward.
Sure.
And so before that, can we have the attendance now, or maybe after your talk we can have the attendance? No problem.
Whatever you feel appropriate, I
Yeah.
think.
So after your talk only will do. No problem.
So hello everyone. Yeah, I mean, I'm just coming here just to have some interaction and get some feedback about the workshop. And but before that, again, I think I thank all the FOSSI CFD team for their tireless contribution to organize this, and also our faculty partners and advisory board members who have actually contributed. I don't know whether Dr. Manavendra is still here, but thanks to all the advisory board members and faculty partners who have contributed to this workshop. And this is done uh, for uh, for all of you. And I also thank all of you for being patient and attending most of the sessions for these 4 days, which requires a little bit of sincerity and also willingness to learn. So, Dr. Manavendra, yeah, thank you very much for your interesting session today. So yeah, I mean, I thank all of you again and again to make this workshop successful. And as I told at the start of the workshop very clearly, that the FOSSI project, particularly this open forum project, has a vision to educate as many, budding engineers as we can from India on open source tools, particularly equip them with the knowledge of CFD with OpenFOAM and other open source tools, and as well as to give them some exposure on what are the real life problems that we can solve by using these open source tools. And I hope these kind of workshop are actually quite um, I mean, they are influential in that sense that I expect that this kind of workshop, those who have attended all the sessions, it might motivate you, inspire you to take up CFD at some point as your career and to apply for jobs in the CFD fields and use tools like OpenFOAM to go ahead in the next stage of your career. And also all the faculty members who have attended this course, I hope it was useful for you to take this tool for education in your own institute and motivate your students to learn this kind of very powerful open source tools and apply the knowledge towards real life engineering solution. And I really hope that you have got a very broad overview of what are the different sectors that can be benefited from the knowledge. And I have to say that from I very regularly discuss with all the colleagues, even from the industry, from India and abroad, and they always say that there are always openings, there are always positions in their organizations, including big organizations such as Airbus, Boeing, Rolls Royce. They are really in search of skilled talents who can solve their problem, right? So it all depends on how much knowledge you can acquire and then apply them to solve real life problem. And I hope this was our first step towards towards basically delivering that kind of commitment. And it is one of its kind workshop in the India, and I can say all with all pride from on behalf of our FOSSI team that these kind of workshops are very unique, and we deliver it for free of cost without any registration fee. Of course, the all the efforts that comes from our team members, research assistants, our managerial teams, they are all funded by the project, which is the funding comes from Government of India ultimately. So it is the vision that we want to reach out to all of you, um, and promote the uses of these open source tools for free of cost, because open source tools are meant to be free. But of course, there is a lot of effort, background work, time spent uh, behind this workshop, because it's a significant amount of work that goes in. So for that, we really have to thank our principal investigator, Professor Prabhu, who has basically given us the independence to steer this project as we feel appropriate for the engineers, and particularly young engineers, undergrad students, to motivate them to use open source tools. And the vision was initially that came from Professor Kannan, who was the primary visionary leader for this kind of project. So we are always grateful to him to bring this idea to India, and it's a very unique idea. And we will keep doing these kind of workshops, keep training all the undergrad students through different fellowship and different internship programs, as Ms. Pyle already explained to you. So if you are enthusiastic, please reach out to us. Please reach out to any of us and contribute to case studies and take part in the fellowship and internship programs. We are also extending our collaboration with multiple engineering schools, or engineering in the colleges in India, how you call it. So, and universities to offer, collaborative modules on open source CFD from next year, which we are planning to make it a national initiative and make it open for any engineering students. And this will be happening in hybrid or online manner, and you can join, and it will go on for 2 to 3 months, and it will be in a structured module or course, which will be, I hope, really useful. We also have ideas, and we will work towards making some NPTEL lecture series and NPTEL course on open source CFD using OpenFOAM in the coming years. So we have many different plans, and we are slowly working towards it. So your cooperation and enthusiasm will really motivate our team to bring it to reality. So thank you everyone, and I think I would now like open the floor for questions. So if you have any particular questions or comments or feedback about the workshop, we are here. Our team is also here. So please, we can take few minutes to try to interact with you and try to answer if you have any queries or comments. So if you want to ask any question, you can raise your hand maybe. Okay, so I see one feedback that need more hands-on part. Yes, I mean we completely appreciate that, but of course you can imagine that the amount of areas that we are covering in the 4 days is immense, and it can be itself a complete course. So we will keep this in mind for future, and but our motive was to cover as much as the breadth that we can cover in different sectors, so that it gives an overview to all of you where we can use open form to solve real life problem. um, but yes, we have plans to make it a more extensive and long term course, and offer them in the national level in the next year. So we'll keep you updated through our announcement.
Okay, so the attendance has been posted. So all of you can mark yourself present. And before you leave, I think many of you are in a hurry to leave. So before we leave, can we have a group photo? Professor Prabhu has also joined. So
Okay.
yeah, if everybody can turn on their camera, then we can have a group photo.
Hello, Professor Prabhu.
Hello, sir. So Professor Prabhu will also interact with the students and all the participants who have joined. So Deepak, could you please help us by clicking a group photo? Some of the a few of the participants have been very enthusiastic and very interactive. Plavan Sen, Rajdeep, and
Yes, ma'am. Yes, ma'am. Yeah.
okay, just say something. Okay, then we'll be ready.
I will count 1, 2, 3. After
Okay.
that, ready? 1,
Yes.
2, 3. One more. Ready? 1, 2, 3.
Thank you so much. Thank you, Deepak. Yes, so we can continue with the questions. I mean, Professor Chandan is here, and then I'll request Professor Prabhu to please interact with the students, the participants. I have the habit of saying students, sorry.
Yes. I think I'm looking into the questions and we'll answer, but I'll request Professor Prabhu to anyway start interacting because other people may leave. So I'm looking into the questions and I'll try to answer them through the chat in the same time.
So participants, Professor Prabhu Ramachandran is the person who is leading the FOSSI team of IIT Bombay. He's a principal investigator. He's a professor from the aerospace department of IIT Bombay. So over to you, sir.
Hi, everyone. So I don't plan to take too much time. I think you've already spent, I guess, a marathon session of 4 days with 7 hours every day of open form. Firstly, congratulations to all of you for spending so much time. This is a non-trivial amount of time, and I'm sure you must have learned quite a bit from this. And also, of course, I'm very grateful to the OpenForm team as well as the extended OpenForm team, that is through the advisory board and all the faculty who collaborate with OpenForm. So this is a really excellent initiative, and it's very heartening to see that there are about 150 people on the session right now, even at the fag end of the whole event. So thank you very much for attending and being part of this. And I really hope that you found this useful. See, one of the things, we don't charge anything for this. One of the things that really helps the team is, if your feedback really makes a difference. So, you can tell the people who've taught you, good things about the things they've done, and also give us feedback, constructive feedback. If you think there are things that can be done better, please do let everyone know. That's always useful. Now, one of the things I just wanted to say a few things which I think would be useful. Again, don't want to take too much time, but I think I want to emphasize the importance of open source software and why we are trying to promote this so much. So if you look at any commercial package, firstly, it's exorbitant, very expensive to buy these. And maybe some of you will be using these packages for free in your universities. So that is because typically your university or some professor or somebody is spent a lot of money purchasing it. And very often these licenses that you buy for commercial tools are subsidized, heavily subsidized for the academic environment. And in fact, this is kind of like a ploy, a sales ploy for many of these companies where they will provide inexpensive licenses in academia so that you become comfortable with it. And then you are unable to move away from their set of tools, and then you go to work somewhere, or let's say you have a startup of your own, or you want to do consultancy by yourself. You are now stuck. You have to now purchase this, and the expense for that is much, much higher. Usually the license costs are skyrocket at this point. And then you're at their behest because now you don't know how to do anything else. You're completely dependent on them. So this is something which we would like to stop. This is not okay. You can always buy. By all means, go ahead. If you have the money for it, please buy software. In fact, if you're going to use commercial software, only buy it and then use it. Don't pirate the software. But for a large majority of us, even when I was doing a PhD, my stipend was so small that buying an international book would be a significant chunk of my stipend. A book that costs $60 would be like a significant fraction of my, monthly earnings. So many of us don't have that ability. So open source software here is something that's a complete game changer. It allows you to download it. Not only download it, you can modify it, you can distribute it, you can share it, you can sell it, and do whatever you want with it. And so people have really put in a lot of time and effort, many years of coding, many years of bug fixing, development, all of this into building this open source software. So there's a large community, many open source packages. Many of you will know about ML and AI. It's the big rage now. One of the big reasons why ML and AI is such a big rage today is because a lot of the core tools for ML and AI are completely open source. So all the big companies, Google, Meta, all of these guys, whatever tools they have built, they actually make it available. So if you see a paper nowadays, you'll find, hey, here's the code. You can go to GitHub, download the code, and actually run the models yourself. Now, of course, that doesn't mean ChatGPT's code is free, but the basic models to do those things, are available, which means you can actually build them, run them on your own hardware. You're not dependent on somebody else. So this really allows people to develop their own things, make progress, and do a lot of useful things. So don't underestimate the power of open source. Can run my laptop is running Linux, which is completely open source. Pretty much all of the tools that I use, open source. So you can basically, have a full career doing work using open source software. And OpenFOAM is one very important part of this because it has a huge number of solvers, has a lot of capabilities. And yes, it's not maybe as easy to use as commercial tools. However, you can run it in parallel without paying anybody an naya paisa. So that is a huge, big difference. So one of the things you will find, many simulations take a long time to run. But if you're going to use a commercial license, they will charge you per core or per machine. And so if you're going to run a 100 core job, finished. You'll have to pay 100x for that license. So this is a problem, whereas open source software eliminates that. Many of you know this, but open source is not just OpenFOAM. There are many other packages, and FOSSEE tries to promote a lot of these packages. So please feel free to use FOSSEE resources. They are all meant for you. Please participate. Please continue to spread this message as well. Please share this software freely with other people because it's completely legal to do it. And spread this very important goal of open source software with your friends and everyone that you know. Right. So this is a great way for our country to also make great progress. Okay, and if you can, please contribute back to these open source packages. So that's all I have to say. We are trying our best to promote open source. Please join us in any way. You can join as an intern, contribute back. Even if you're not joining through FOSSEE, it doesn't matter. You can still contribute to OpenFOAM and any open source package. Okay, so please remember, it's a global community and you're essentially becoming a part of that global community. So
So
thank you very much. And if
thanks,
you have any
Dr. Vinay. Yeah.
questions, I'm happy to answer them.
Sure. I saw that there are no major questions in the chat, but I just wanted to add one more point towards it, towards the importance of open source. So, I mean, I often, when talking to industries, particularly global industries, and I'm basically kind of trying to do a movement to make it a business case to different commercial organizations to let them understand the power of this open source tool. So one thing that I've come up with, I mean, I have understood, I think I've mentioned it many times in different forums, that many of these commercial organizations or industrial sectors, they think if we are giving them a tool which is free, which means that they are not accurate enough. So this myth can be only broken by a proper framework of verification and validation. So when you are basically trying to use these open source tools, please give a lot of importance on verifying your different parameters of, for example, in this case for CFD, you need to verify or do a proper quantitative verification of CFD schemes, the cell size, time step size, any other stability criterions, everything. So do not underestimate that, particularly at the early stage of learning CFD. So do not think CFD is just a colorful fluid dynamics. You can take these case studies and just run it and produce nice contours, but that's not the end story of it. And that is the only way that you can convince others that it doesn't matter whether it's an open source tool or a commercial license tool. It matters whichever code you use. You need to understand that the criteria that you are using, or the input pre-processed geometry and mesh that you are using, are properly verified, and they are not sensitive, the solutions are not sensitive to any of these parameters. And equally, validating with the experimental results cannot be underestimated. So there will always be need of carefully carried out experiments to give us results, to test our codes, to validate our results, etc. So just wanted to mention that if basically somebody just come up with this argument, you can always justify your results through an appropriate verification and validation study, and do not ignore that before going into a lot of colorful pictures. Yeah, so I just wanted to add that part.
There was one question in the chat box. Kamalesh was asking that are there some other open source alternative tool for CFD apart from OpenFOAM?
Of course,
So
there are many. So if I can answer, so basically, as you can see that most of the formulation used in OpenFOAM are for incompressible flow. Not everything. There are compressible solvers such as row central foam and other things, but OpenFOAM formulations are written with a focus on incompressible formulation. But there is another popular CFD code which is called SU2, which is developed in Stanford. And basically they are equally have a big community, and there on the other hand, that particular solver or formulation of that code has been done keeping in focus of compressible formulation. So they are very good for compressible flows, but they can also be used for incompressible flows. So I would say SU2 is one example. There is Python based PyFR. There is immerse boundary based open source code developed in Imperial College London called XCompact 3D. There is Nectar++, and there are many different examples. So if you would like to basically know more, you can reach out to us. And I think it's a good idea that in the FOSSI website also we can actually have a tab on all the other different open source CFD codes apart from OpenFOAM. So yes, in short, there are n number of open source option to do CFD simulations.
And just to add to that, there are also, finite element based whole bunch of
Yes.
concepts. There's Phoenix, there's
Phoenix, yeah. So there are many different options.
yeah.
Yeah, so Payal or anybody you'd like to add something about GUI, that we are developing that part also? I think,
Yes. I think you only can, tell.
I mean, I think Professor Prabhu is more knowledgeable in that respect to me. But
OpenFOAM
in
GUI.
short,
Actually,
in short, basically, this is just an overview. I can tell that, of course, one of the major lacking in this kind of open source CFD codes is that which has pros and cons. I would say the pros is that you are forced to go into the source code and understand the code, but in the commercial level or industrial scale, we do not have the timeline that everybody would basically go into the code and understand every piece of algorithms that is written. So in that case, the commercial softwares, they have a very well built user interface or graphical user interface, which really helps. And I think you have seen the presentation from Panduv applications by Advait, where they have taken OpenFOAM and then overall they built their own user interface for additive manufacturing, and now they're using and they're kind of selling the idea to different organization, national labs who wants to do additive manufacturing simulation. So we from the FOSSI team, we are also very much eager to develop a user interface which will ultimately help the beginners at least to cross the knowledge barrier or the hurdle of steep learning curve, setting up the meshes, control parameters, everything, which is not a very easy task. So we have dedicated interns or dedicated team members who are actually from the computer science background looking into the possibilities and developing. We have some version already released, and we maybe in future we are also going to maybe organizing a workshop on showing the demonstrating the capabilities of that GUI version. But we also accept internships, fellowships on the development of GUI in every call, where if you are from computer science background, if you want to develop that user interface, you are very much welcome to reach out to our team and contribute to the development. And the recent version is called Venturial, right? If I am correct. Yeah. So the recent version is named as Venturial, and we have very quite a few talented interns who has contributed, developed that user interface, and we are still working on it. So please reach out to us if that is of your interest and you want to contribute towards that.
I can show them the resources that we have on OpenFOAM GUI. So basically, if anybody who has a background of Python and FreeCAD, please connect to us. We actually are looking for good people who can contribute in the OpenFOAM GUI part. Yeah. So, any more questions for Professor Chandan or Professor Prabhu? Is Venturial GUI for OpenFOAM? Yes, so Venturial is the name of the software. It's a GUI for OpenFOAM. Yes. Let me show you the resources. Yeah, Prabhu sir, you want to add something?
No, I'm just,
Hey.
someone is
Okay.
asking, can you do a project in answers with guides in FOSSI? I replied saying no. So I don't know if someone is just trolling us, but okay. That's
Okay.
Yeah, and Venturial is a GUI for OpenFOAM. It's currently still under development. So, but I believe there have been there were some workshops they've done, but at a limited scale, just to get some basic feedback.
Yes.
Yes, sir. In its current stage, we are, at least in the new update, we are able to create a snappy hex mesh dict also. Previously, it was
Okay.
only for block mesh. So now it's snappy also.
That's good.
Yeah. So maybe soon there will be a.
Yes, sir. Suit.
Okay, please don't put any unnecessary comments in the chat box. Otherwise, we are going to log the chat. Okay, so let me share my screen and show you the OpenFOAM GUI that we have, the resources that we have. Is my screen visible?
Yes.
Yes, ma'am.
Okay. See, these are all the information on the OpenFOAM GUI part. We have some tutorials on Python. So Venturel was developed using Blender also. So we have all the tutorials here. Just after the workshop, or maybe tomorrow, or whenever you have time, just go through all these resources. FreeCAD also, we have some resources. And if you're interested to contribute in the development of the GUI for OpenFOAM, you can write to us. Okay, with this, I think we can proceed to the last section of the of my presentation, which is the vote of thanks. Okay, so here I express my gratitude to IIT Bombay at first for providing us this opportunity to carry on this FOSSEE project at IIT Bombay, for providing us all the resources for this project. We are also thankful to Ministry of Education, Government of India for funding this project. And we are thankful to NME ICT, the mission for which this project is working. We are really thankful to Professor Prabhu Ramachandran for leading us, for leading the FOSSEE project. We are always thankful to Professor Kannan Modgalia because he was the person who actually gave me the idea to me and Professor Chandan that we can have an advisory board like this, and people and the learners who are coming to FOSSEE, they should be aware of what all is going on in the industry at present, the CFD industry at present. So that's how the idea came to us, and we are here today with a proper advisory board. And last year we had this launch of the advisory board, and we had a industry academia interaction session on OpenFOAM. And this year we are having this workshop on industry readiness. And thanks to Professor Chandan, as always, for leading the OpenFOAM team of FOSSEE. I'm thankful to my colleagues, Ms. Usha Vishwanathan and Ms. Vinita Gavri, for being with me. For being with me and helping me to arrange this workshop. Thanks to Ms. Preeti. Ms. Preeti Guikar has helped me to organize and help me with all the logistics, like the attendance part, the promotion part, everything. I'm also thankful to Mr. Kushal Singh Rajput, who has helped me with all the promotional materials so that I could have. So I actually use many posters and many social media posts to reach out to all of you. So without Kushal's help, it was not possible. So a big thanks to my team members, Mr. Evan Fernandez, Mr. Paris Palkar, Mr. Manjil Situla, Mr. Nikhil Chidnavis, and Mr. Pranay Pandey. And thanks to our e-studio team of IIT Bombay, Mr. Deepak, Mr. Kailash, and Mr. Pradeep. And here I would like to express my gratitude to all the advisory board members of the CFD team of FOSSEE, especially to Mr. Pushkar Sheth, Mr. Nikhil Bamare, and Dr. Manavendra Dey, because they have also guided FOSSEE interns, and they have published the projects in the form of case study or research migration. I'm thankful to Mr. Harish Jairaj, Dr. Joseph Prabhu, Mr. Advait Gupta, Mr. Ranjit Desai, and Mr. Arnab Chakrabarti, who have delivered excellent lecture sessions during this workshop. So with this, I'll just end my talk. So here goes the email ID. You can just note it. You can also click a photo. So cfd.fossee.in is our web page for the CFD part, and fossee.in is our parent website. So I'll just stop sharing the screen. Okay. So before we say bye-bye, any message, any questions, relevant questions? Thanks. Thanks a lot. The pleasure is ours. So I think we can conclude the session. Okay, as I said that it's just a beginning and not the end. So with this, I say bye-bye to all of you. Thanks a lot for joining. Yeah, thanks, Dr. Bye-bye.
Bye.
Thank you, everyone.
Thank you.